How do I view my fucking repositories?
Dfa tool. Go.
Soon. IPL SDK. GPIO. The header. So, yeah, so we are using the correct GPIO port. So, I'm gonna go under the assumption that it's hashtag fucked. And we'll do some
Okay,
DFA.
chat now for the fun stuff.
Yep, so
Let's go.
we just managed to hack the PSP. We got a bunch of we got a bunch of faults
Yeah,
out.
let's cut
Woo.
the first hour from the VOD.
Yeah.
Okay, so cool. Now that you
Oh,
hacked
we've
the
had some
PSP,
we had
you
some
got all these
downtime, yeah.
samples. That's so cool. Unfortunately that video was lost, but you just have to imagine
Yeah.
the
Just have
PSP hacking. So now what are we gonna do with these samples that we've
Alright,
just
so we got a
collected?
bunch of samples, so we need to go to my GitHub and we're going to go get DFA tool, which is a really cool tool that takes all the samples that we just got and should hopefully spit out a key. So if we
Do you want
clone
to pull it
this,
up on VS Code?
yeah, and we clone it here, get the VS Code. We don't need this anymore because we've hacked the PSP. Yes, please configure. Use this. Allow. Don't always configure. And hopefully it builds.
In before 2 hours of trying to get this to build.
Control reaches end of non-void function. Huh?
It's a warning, who cares?
Yeah, it's a weird
Who
warning.
cares?
Oh, okay. Yeah, it's not even possible. Cool. Alright, so we did it. So now we have this code and we should test it. So
Can we walk through this code?
yeah, we will, but we need
Like what
to
it's doing? Okay.
yeah. We need to get our faults. So we got some faults for one of the PSP keys. I think it was 42 or 44, something like that. So if we got these bad boys.
Can you briefly tell us what those are?
Hang on.
What?
Yeah, okay, so we got a bunch of faults. These are so what we did was we glitched the PSP as it was doing a decryption. And we got these results out. So what we're looking for is that these have a fault in round 8, which is the second to last in the AES life cycle. So if we look up a simple AES, what would you call it? AES algorithm
So
diagram.
can you be more clear and
Mm-hmm.
talk about what those numbers are, what they mean, and how do they correspond to a glitch?
What do you mean? What these numbers mean?
Are they hashes? Are they
No, these.
like
Okay, so this is just a decrypted output from the PSP. So we've told the PSP, okay, do a decryption of zeros with this key, and this is the result. This is the I guess technically the plain text. So if we say this, right, we got the PSP, we got AES, and we got out. We've told the PSP, put a bunch of zeros, does the decrypt, and we put like a glitch.
so you're trying to encrypt all or
Decrypt.
decrypt
Yep.
all zeros with a unknown key that
Yep.
is
We
stored
don't
in
know this key.
hardware.
And we put a
And
glitch in the middle.
if without a glitch, it would be one of these, or it's not listed here. Is one of these
Actually,
the correct result?
I don't know. So
Okay,
the answer
well,
is no.
okay.
The answer is no. I don't know what happened, but one of these isn't the correct result. These are actually 3 faults that without the correct result, or it used some input that I don't know of. But
Okay.
the main thing is they're consistent with each other. They have the same input, right? So it might not be all zeros. It might be something else.
Tim Star asks, how do you know that's in round 8?
Okay, we'll get to that. But the idea is that we have some input. We have the AES with an unknown key. Then we insert a glitch during it, and then we have the output, which each of these is one of these outputs. They all have the same input, they have the same key, but they have very similar glitches, and we get the outputs. How do we know it's in round 8? Okay, I actually have a picture that can help us here. But the general idea is we know it's in round 8 because of trial and error. So this algorithm uses it's not AES. Okay, so the reason we can figure out where it is we can do it with a known key, right? So for the PSP, half the keys are reversible, and some of the keys are known. So we know the values of some of the card keys because of other sort of PS3 related things. So what we can do is we can start glitching on those ones and be like,
The
okay,
known ones.
a known
The
one,
ones with the known keys, yeah.
known one, and a known. We can start glitching with a known key. So we can reverse it and see where the bit flips happen.
By reverse it, you mean that you take
We
your faulted ciphertext and you try
Yep,
to write in the inverse AES
exactly.
operation.
As well, not quite the AES inverse operation, but yeah, you kind of rewind the decryption steps, right? And eventually you'll get to a part where what you could do is you do the encryption first and you take all the intermediate results between each rounds, and you can compare and see when the bits are minimal, and that's where the fault is.
So when you say when the bits are minimum, you mean that in the state, if you XOR your
Yep,
expected state at that round
with
versus what you actually observe from your
yes,
faulted text, then you will see only a few bits flipped.
yep.
But
You're looking
if
for
you
a few bits, yes.
but because of the diffusion property of AES, if you keep reversing
Rewinding,
AES
yep.
rounds, rewinding AES rounds. So basically, the way AES works is, it try if like one bit difference, it tries to diffuse through all the bits, right? So if once you start rewinding round after round, let's say you have a fault in round 5,
Mm-hmm.
so you're gonna see like about half the bits flipped in round 9, and then about half the bits in round 8, and so on. And then at round 5, you're gonna see like maybe 3 bits flipped. But then if you try to rewind it one step farther, then you're gonna see like half the bits flip again, just because you're now like doing another AES round. So you're gonna only see one round where there's like only a few bits that are flipped, and then every other round you're gonna see like most of the bits flip.
Yeah, so you're probably going to see, yeah, it'd be obvious enough because most of the time you're going to see like a lot of bits flipped, right? Just the way AES works. So you're going to see something that's unusually small, and that's likely where in the round that this glitch has happened. The other way, I managed to kind of this is not specifically to find which round in the AES, but to find out if I was even glitching the AES. Is that the decryption operation on the PSP isn't like a just a straight AES op, it's a CBC one. So I could also see reflections when it does the XOR. So if I pass in 2 blocks, right, all zeros, you should expect the same output, right? Because when you're doing decryption, it XORs with the ciphertext. So zero XOR with anything is the anything. And what happens is if you glitch that XOR, you see reflections in the input. And if you get the one at the end, you see it in the output. So that's how you can find the start and the end of where the AES is. And then from a power trace, you can kind of gauge. So the rounds are pretty much the exact same duration. So you can kind of have an educated guess where about you would expect the round 8 to be. And then you can just do very small tweaks from there, yeah, and then confirm with the whole uh, rewinding the decryption, comparing, find the smallest number of bits and targeting there. That's pretty much how we did it. Power trace means you're using a scope. We're using just the chip whisper scope, yeah.
Yeah, there is a scope on the chip whisper.
Yep.
It's pretty useful.
So we have a shunt installed on the power input to the PSP core, so we're just measuring off of that. How do we know glitches are
Okay.
similar? Okay, yep.
Can
Yeah.
you run this and
So yeah, let's
show us
run
the
this.
magic result?
So we then go, okay. So what we know is it's a decryption, and we're targeting round 8. So we pass in faults. I can't even read my own code. There we go. So it finds the key really quickly. And this is nice, but how does it work? So let's look at code. This is C++ magic, so we don't really care about this. This is just like boilerplate stuff. It reads in crap. The interesting stuff is when we get to these solvers. So
That's faster than DPA. I mean, yes, in an ideal DFA situation, you can only get 3 samples and crack the key completely with it. But it is much more difficult to put in to perform a DFA attack in the grand scheme of things, because you need to be able to uh, pass in glitches at like very precise rounds.
yeah.
And you like the way that this is achieved is that we manually control both the clock and the power line, so we
Mhm.
make sure that that it's
Super
synchronized.
precise, yeah.
Yeah. And then we slow down the clock, et cetera, et cetera. But just on a random old target, that might not be possible. The DPA is a lot more general. You can you know you can do it without modifying the device at all. You can just like passively listen. Like sometimes you can do it without even taking the device apart. I've seen DPA done across the room with an antenna. So
You've seen DPA done with an antenna across the room, did you say?
yep,
Cool.
on a Intel processor.
Mm.
Yeah, it uses a lot of like if you're doing encryptions that like on like an x86 processor that uses a lot of power, um the so this goes to a bit more technical details in how transistors work. But when the transistor's switching, there's this I can't remember the name of the effect, but it kind of overshoots up because of the all the power like rushing in at once. And you have to uh the capacitance is equal to dV/dt and inductance is equal to di/dt or whatever. But basically, it creates this like little sharp spike in a transistor, and if like thousands to millions of transistors are switching at the same time, then they all spike at the same time. That is actually that creates the necessary conditions for an antenna to transmit um, energy. So if you have like some sort of antenna structure within the SoC just by chance and these spikes happen, it will actually like shoot out EM waves and then you can measure that with an antenna.
There you go. Lasers and shit. Okay, so
Yeah, Tim Star says EM side channel. That EM side channel is actually different. That's EM side channel is actually more applicable. You don't even need antenna effects. You just need the electromagnetic fields, which is on everything. The thing I'm talking about was the antenna. It's only possible if you have high power usage and antenna structures within the chip. But you can do it from like across the room. EM, you have to do it like almost like touching the chip with your probe.
okay, are you done, Ethan?
Yeah, back to your regularly scheduled template
Yeah,
type
yeah.
name
Ignore the templates. It's not
decoding.
important here. The main idea is we have the solve R8, right? In fact, let's get the paper open as well because I'm going to reference it.
Maybe you want to explain the R9 stuff first
Yeah,
before
yeah,
you get
yeah.
to the.
I'm exactly, yeah.
Okay.
So the attack isn't actually on an R8, right? It's on R9. It just so
Round 9.
happens that you can convert round 8 faults to round 9 faults easily. C++ is cool, but who uses streams? Come on, bro. Come on. Stop pretending. Everyone
Tim
uses
Star, I can't.
streams.
Tim Star, I can't hear you over the template type name std.
Let's not be rude. Let's not be rude. Right. I want my i3 back, honestly. Okay, this will have to do. Okay, so this is the paper that this tool's based off of. And it's it's a PhD math kind of thing, but we will just go over like so it's got really good diagrams in it and stuff and some nice examples. But the
He says dismissively.
yes, for myself, sorry, yes, it's got PhD math shit that's just too much for me, right? This kind of shit, nah, not me. Me, Davey, me simple, me like nice pictures of matrices. And this is a really nice example too. But okay, so the general idea of the fault, that round 9 fault. So this is what this is about is you have your expected input, right? This one here. And a fault gets injected. And what happens is it goes through the mixed column part of the AES. In fact, let's get the AES thing here. Where's the really nice one? This one. Okay, see, look. So each AES round, you XOR a round key, you do subbytes, you do shift row, you do mixed column, and then repeat. You do another round key at the end, all the way up until the final round, which is round 9.
And each one of these steps does some sort of linear transformation on your state matrix.
Yes, yes. These are all linear, except from the subbytes. So all that happens is it goes to mixed columns. So this is talking about this last one here, right? Oh, okay, not this one. This is talking about the last one of this one and this one here, okay? So it's the second last and the last step. So this is the second last step. It does mixed column and then it does the XOR with K9, right? So what we're seeing here is a fault. It goes through mixed column, so it propagates down the column. And then it's XORed with...
I think you should back up a little bit. So the first gray box, so in the second matrix, right, where it says fault injected 1E,
Yep.
you see one gray box on the very first cell. So
Yes.
that is where the glitch
Yeah, yeah.
happens, right?
This is the glitch. Yes.
Okay, so now explain why the next one has 4 gray cells.
Yep. So the mixed column step, it just does a multiplication over the column, right? So this whole thing here is just a bunch of equations. You know, it's like a. It doesn't matter the exact matrix math, but yeah, it's just like a linear transform across the column. And then it's an XOR with the key. So we see this bit, then we get to the key, and then we're on to the final round here.
And this key we don't know
We don't know the
in
key.
practice, right?
Yep.
Yeah.
We don't know any of these keys, so both K9 and K10. So what we see here is after this XOR, we have this. So you can see that it's still only these 4 values that are dirty / affected. Then we have a subbytes again. So this is just a straight, what would you call it? Mapping. Subbytes you can just view as like a direct mapping. One byte goes to another byte. It doesn't matter which byte,
Yeah,
but
so
you can.
1-to-1 mapping.
It's 1-to-1, yeah. And then shift rows just literally just moves them around. So at the end, right, and then you have an XOR with an unknown key. At the end, a fault in round 9 represents itself as only 4 bytes modified. So you see here it's 1, 2, 3, 4.
So I think the important thing is, so like when you're looking at an output of an AES in like ASCII form, right? You just see 32 characters.
Yep.
These 32 characters are basically written in a 4x4 matrix. So you can imagine the result as this matrix like written in one line, and you will see that exactly 4 of those bytes are different from if you were to just perform the encryption correctly.
Yeah. So yeah, but if you wanted to make this, so this is for round 9, yeah. Without going into details of how this works, I'll just quickly mention how you can get a round 8 into a round 9.
Look, before that, why don't you explain why having this is enough to recover the key, or at least the intuition behind it?
Okay.
Hello, Pluto.
I don't want to. I feel like I'll be opening a whole nother can of worms here.
I mean, I think that's the important part. I mean, the round 8 to round 9 transformation isn't important.
Yeah.
The important part is how. So okay, so you see here in the end, right? You have a result where 4 of these bytes are tainted
Yep.
due to one glitch in round 9. You also know separately the 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 ciphertext where there is absolutely no faults.
Yep.
So you can discard all the bytes that didn't change, and you only look at the 4 bytes that are different. So from that, somehow you can make predictions on the key, and I think you have a lot of code that does
I do
that.
have a lot of code that does that. Yeah.
Yeah, I think that's the important thing that we have to talk about.
Yeah. Sure. Okay. All right. Let's ignore under Ethan's request. We'll ignore round 8. We'll just talk about round 9. But the general idea is that it's trivial to convert a round 8 fault to a round 9 fault. And then what happens is we go to solve round 9. And solve round 9 is this here. Let's see if we get this bigger. Oh no. I'm using all my i3 shortcuts. Actually, we could just get this smaller.
Tim Star says Davey must be an academic.
Ha. Ha ha ha. Ha. My biggest complaint of this was decoding all the academic stuff. All right, so we have this solve round 9 candidate. So, oh, it's been so long since I looked at this code. Okay, so differential fault analysis implies that you have a differential. So the idea is that if you analyze the difference between two inputs, so we're assuming we have two inputs here. We have a reference, which is our oracle or reference. It's our known state. It's usually like just the decryption straight through with no glitches, right? So in this case, it would be without fault. So these would all be expected values. The round 9 faults is obviously our faults. And what happens is we go through the code here and we go through each fault and we create a differential fault thing. And that's just an XOR between a fault and that. So we have this, then we XOR it with the reference. So that leaves these 4 bytes only. Yeah, all these ones highlighted here, they're the only ones we get. And instead of having these values direct, we have it XORed with the expected ones. That's their differential. My
So
math
quick
prof always says
footnote
trivial.
here, and since I don't think this was mentioned, was the round 9 fault. We can only recover 4 bytes of the key.
Yeah,
So the stuff in white,
it's fine. Yeah,
we
I'll
don't have
get to
any
this.
information for.
Yeah,
We can only, so we have to do multiple variants of this attack. But so right now we're only focusing on the 4 bytes highlighted in gray here.
yes, yes. We were only focused on 4 bytes. And yeah, Ethan's right. That'll give us. That could only give us 4 bytes of the key. So if we go look at the paper again, it's very mathy, but you can see that it goes like this is just a more matrixy description of what happens here, right? You got your fault, you have your mixed columns, and that just it starts showing a relationship between what happens in the mixed columns and the error. So this is assuming the differential, right? So all these are 0 because we don't care about them, right? Then we have a relationship. We have 2 times the error. We have an error, and a 3 times the error. Then you see that the round key doesn't really change anything. And eventually we have a bunch more stuff. We have the error through the subbytes. We don't know the value of it. We don't know the value of the error either. And this continues all the way through until we get to this point, which is where we're at now. We have 4 bytes. The rest we don't care about. They're all zeros. This is the XOR. So yeah, like as it says here, output with the faults, output without the faults. We've XORed it. This is what we've got here. A differential fault. Fuck. Alright.
So so when the matrix you saw earlier, that is how is that related to the XOR you were talking about, Justin?
These matrices?
No. So back to the paper. So you didn't explain like what these mostly 0 matrix these are. You just said these are the faults, but I
So
don't
yep.
think people can
These
understand what that means.
okay, yeah. So my point is, right, we don't really care about anything other than the faults. Everything else we can disregard. Like we are focusing only on these 4 bytes. And this is just a more mathy explanation of what's happening here, right?
So these matrices are just the XOR
Yes.
of the correct state matrix at that point and the faulty state matrix at that
Yes.
point.
Exactly.
Right.
So then it gets proper crazy with the maths, but we'll talk about this through the code instead. I think it's easier, perhaps. Let's see. Where are we? Okay, so it generates a fault, and all the fault is an XOR between the fault and the reference. Okay, so that gives us our differential. And this is just the final output. So we don't have like round 9 information at this point. We just have the final output XORed, and we have 4 bytes in a various formation similar to this, right? So we'd have this one, this one, this one, and this one. So from that, how do we actually see about getting keys? Or getting a solution closer to getting keys? Well, you see I've got all these group things.
Okay, so sorry. So I think I will be the viewer here because I haven't honestly gone through this code either. So
Okay,
how about I just ask you about
sure.
how this code work, and then you can answer, and that might be easier than you trying to
Yeah,
jump all over the way around the code and have no idea what's going on. So okay, so in line 40, you have differential fault, blah blah fault. Is
yep,
this the creating the XOR between the
yep.
reference and the
This
R9
is
fault?
just creating the XOR.
So so that corresponds to the 3.4 example, right?
Yes, this is
Where
this
on the
example right
paper.
here, 3.4.
Okay, cool. So okay, so back one to or like in your code.
Mm-hmm.
So after that, after you created this fault thing, can you talk about what is group affected? What does that mean?
Okay, so a key is for AES128 is 16 bytes. We get 4 bytes per group. So a grouping is a certain arrangement of this structure here. Yeah, we get 4 bytes per
Mm-hmm.
grouping. So we need 4 groups, each giving us 4 bytes. So
Mm-hmm.
what we're doing here is we're trying to figure out, okay, which 4 bytes are we expecting from this?
I see.
So if we look at the code here, is group, it is looking up, it's effectively looking where the non-zero values are, right? So
Right.
if we go to this structure here, so it's going to be decrypt. Fuck. Actually, let's do it for the perspective of encrypt so it can matches the paper.
Right.
Yeah, the only difference between encrypt and decrypt is a small amount of structuring. So
So in 3.4 we have, does that correspond to mask 3? No,
mask
mask
2.
0. Mask 0,
Mask 0,
right?
mask 0, yeah.
Yeah.
So all this is the index in the matrix where we expect the fault to be. So if we look here, right, E7, that's 0. If we then look at the next fault, we expect it to be at position 7. So that's 0, 1, 2, 3, 4, 5, 6, 7. Okay,
Right.
simple enough. Next one's 10. The next one's 13. We're just checking, right? Are these values non-zero? And that's where we're expecting the differential.
So what happens if you observe that it's not in one of these 4 groupings, your
If it's
faults?
if it's not one of these 4 groupings, we can't solve it with this algorithm. It's not. It can't be modeled with this attack.
Right. So it probably means that you corrupted a different
Yep,
point than round
exactly.
9.
Yeah, it's not. It doesn't fall under this attack.
So
So,
it'd be safe to say that every 1 byte corruption in round 9 would correspond to one of these forms.
yep. And if you look here, I don't know how easy it is to see in the code, but you can make out the same shape, right? So wherever there's an F, maybe if I highlight all the Fs, and
Mhm.
wherever there's a 0, you can see like it makes the same shape. So
Yeah.
you got the one in the top left. So this is group 0. Group 1 is got faults like this. Group 2,
Yeah.
then group 3. Easy.
This actually corresponds directly with taking one column of Fs and performing the shift row operation
Yes.
um for each row.
Yes, exactly.
So like if row 3 is all or sorry, column 3 is all Fs and you do the shift rows operation, then you will
You'd
get what
expect
mask 3
this.
looks like.
Yes.
Yeah.
And for decrypt, it's the exact same concept, but inverse. But we'll keep looking at encrypt. So if we go back to this code here, we have the is group effective, and yeah, it just looks up each of these things for the group and checks they're non-zero. And really what we should be doing here, and what I'm not doing, is I should be checking that the rest of the bytes are 0. So this isn't completely to spec, because like, yeah, as Ethan said, like if we had an output here that was mostly all 0, but maybe this one was non-zero, this would still pass. So it's a bug effectively.
Right.
But the important thing
So like
is,
if your code is more robust, you would have like an assertion here, right? That's
yes,
like
something like that.
assert no zeros for us. Yeah.
Yeah. So then we've got the key candidates, which is it's a collection of 4 fault candidates. We've got 4 groups. We've got 4 fault candidate lists, and the fault candidate list is basically, it's just a set that says, okay, have we what potential solutions do we have for this key? We'll talk about more about that once we get closer to generating the candidates, but there's
So
no
the
point.
logic. So like line 42 is is it saying basically like, hey, if the fault I'm looking at is, corresponds to group 0, and I've already solved it,
Yes,
then it's
there's no
pointless,
point.
right?
Yeah.
So because I'm collecting like a huge set of samples, like
Yes.
thousands, right?
Yes.
So there's going to be a lot of like useless samples because we already used these to solve the key, so we don't need to solve the same part of the key again.
Context for all O equals 0. Yeah, you like that? I think
God damn it, where's that?
it's an encrypt
Oh my
here,
god.
because
No way,
before,
dude.
when I was using the
Oh
the
god.
the Intel intrinsics to do the stuff, I needed to have it as
Uh,
integers. So I
dude.
think this one, this one's updated properly, true and false.
Was it explained why the minimal of 3 faults is required? I think we will get to that at the
Yes,
end.
yes,
Right now, let's just focus on like like one fault.
yeah.
And
So we get to a group, we check if the fault belongs to that group. If it is, and it's not solved, we then be like, okay, let's try and calculate all the potential solutions for this fault. So one fault doesn't give us all the solutions, right? It gives us a huge set of like, okay, it could be this or it could be that.
yeah, let's dive into this code. Yeah.
So for each group, okay, yes, I remember this. So we're going to calculate the candidates for a group. So we have the group number, but we have to calculate it 4 times. 0, 1, 2, 3. And this is because if we go back here, you see here where the fault's happening? It's happening in row 0.
Sorry, can you quickly hover over candidates for fault so I can see the name of the parameters?
Yep. Fault row. I was
Okay.
about to explain this, yes. So
Okay.
you can see here, this is in row 0. And as it goes through, the mix column affects everything in the column. So what happens if you have a fault here? Well, you'll see that it'll still have the same result here, right? It'll all be, these values change, but the only thing that changes is these constants, right? I'll talk about
And
this soon.
why? What are those constants and why do they change?
These constants are the matrix constants for doing the AES mix call. We'll get to that in a second. Literally a split second. So
Okay.
all these numbers here, that's just specifying the rows, because when we have a fault, we don't know unless we have a really good idea of our target, right? Maybe our glitch is very specific and we know which row we're targeting. But if you don't, you have to just assume, right, okay, it could be a fault here, a fault here, it could be in any one in this column. So what we do is we generate candidates for each column. And if we go here, Yeah, okay. Let's talk about the mixed column matrix. I think there is a whole wiki page on the yep. Okay, so all we have here, a mixed column is just a multiplication using this matrix here. Okay, so
Right.
if we go back to the paper, we see it's 2113, which 2113 for the column. And for each row, you just move it along.
So it's important here that the rest of your states you assume to be 0, right?
Yes, yes, you absolutely have to have the rest of your states 0 under this assumption, yeah. So a fault in this byte and this byte, you cannot figure out what's going on. It has to be that it's a single fault in one of the rows here. It can't be two faults. It has to be only one fault. Yeah, so all that we're doing is, so if we go to this here, you can see that we've got the fault row. I'm doing this thing again. We go to encrypt. Our mixed column matrix is just the same as this. So we've got 2, 3, 1, 1, 1, 2, 3, 1. You know, it's exactly the same. And the row basically just changes the way the constants are laid out in the final multiplication. So we assume everything else is 0, and we get different values for this. You can, what is this? One fault gives you 4 bytes keys of a group. There are 4 groups in total, 16-byte master key. You need 3 different faults to get 12 bytes. Master key, last 4 bytes you can brute force if you assume every fault is exactly 1 byte and you have 3 distinct fault groups. You only need 3 faulty outputs since you can use the other good bytes. You can. Yeah. Yeah, okay, yeah. I see what you're saying. Yeah, but we'll get back to that. This is more to do with the 3 faults is more to do with the round 8-ness rather than the round 9-ness. But yeah, you could theoretically solve 3 of the groups and then brute force the last group. Where were we? So we're calculating fault candidates now. And this is where it gets
Can you
hairy.
explain what you mean by a fault candidate?
Yep. So a fault candidate is literally a possible value. It is, I guess,
A
it's
a guess for a byte in the round
yep.
key.
It
Okay.
in this case, it's a guess on this exact value here. What is this error value? It is like, okay, what could this error value possibly be? And the reason why DFA works here is if we go to this function here, generate X to Z map, and I'll explain what X and Z are in a moment, but the whole reason this works is these multiplications, it means that only a certain set of numbers can kind of fit that description. Like, trying to figure out the best way to describe it. It's like if you have, like, mathematically, I don't know how to explain this simply, but I guess,
How about you scroll in the paper to the linear equations?
yeah, simply. Linear equations, this one.
Yeah. So, yes, yes, yes. So, I guess the way I intuitively see this is that you basically have a system of equations that is underrepresented, and you're using guessing and the linear properties uh, to find out what the unknown variables are. So you don't know here. You don't know E. and you don't know the
X values.
yeah, you don't know the x values, but you know s of x, s of x plus, blah 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 times e, and uh, from that you can also figure out what the e primes are, epsilon, whatever, right? And
No.
the
We know the E primes. We know these values here.
right,
We don't know everything else, but we know
yeah,
that these.
the epsilon primes are the values you get by XORing the correct state and the faulty final
Yes,
state,
yes, yes, yes.
right? Right. Okay. So, but basically, it means you know like everything here except the x and the epsilon without the prime.
Yep.
But you also know the dependencies of these equations, right? So you have like x plus 2 epsilon, x plus epsilon, so on and so on. So it's basically just, I mean, it's not exactly this, but it's basically kind of like solving linear equations, but with a little bit of guessing.
Yeah. So because of these multipliers and having the same constant, you can start to narrow down the search space for a single solution for this value. Right, because
Yeah.
some values uh, of this
Just
epsilon
won't
just
just
won't
won't
work.
yeah, won't meet all four equality.
Yeah. So,
So, I guess it's also important to point out that there's only 256 possible
yes.
values for epsilon, right?
So what we have here, what I'm calling Z is what am I calling Z? Let me double check. Okay, so Z is wait, Z's epsilon in my case, right? So you can see here the equation we have y equals s of x with s times c times z uh, s of c times z plus x. So we have s is the subbyte function here, same as this. X is the various x naught x value or whatever it is. So depending on what part we're doing, it would be x naught, x1, x2, or x3. C is the constant value, so it's going to be 2, 1, or 3. And Z is our epsilon. And this is all in the... Oh, how do you pronounce it? The Galois? Galos?
I just say
The
GF2.
G...
I don't
Yeah,
know.
yeah.
Yeah,
The
the
GF.
gallows field
Yeah, it's
of
GF. So it's not...
under 2,
It's
yeah.
not... This is fake multiplication and fake addition. It's not important, but just let it be known that this is XOR and this is a special multiplication. So what I do is, right, I'm like, okay, so if we calculate the Z or epsilon here, and have a mapping of X values to Z values, because if we can calculate all the possible values of Z, we can then figure out all the possible values of
So is this a optimization by doing pre-computation, so you don't have to like do this like equation that you wrote in the last line of that comment? You don't have
uh,
to
I would say
do that,
in a way yes, but it's a simplification because the search space is only 256 values.
right? Yeah.
So all we do is we rearrange this equation here, right? So we can solve it for epsilon instead. We know epsilon prime. We don't know everything else. And what we end up with is a mapping of these x values to these epsilon values. The
Right.
math here is a bunch of XORs and a bunch of table lookups, inverse box, and GF multipliers or inverse multipliers, depending on
So
the algorithm.
if I take a step back,
Mm-hmm.
is what you're trying to do here is you're trying to say like, okay, at some point I'm gonna have to start guessing the keys, right?
Yes.
And for each key guess I make, I have this, I can use this table that's generated to say like, okay, these are the epsilon values that could be possible if this is my key. And then somehow you can, take all your guesses and like, combine the possible epsilon values in order to see if your key guess is right. Because if you say like, okay, I'm gonna guess, this byte of the key is this, but then it doesn't work for like what, like
Mm-hmm.
you're gonna, like, if you guess x is some value, then epsilon has to be some other value. But if 2 bytes don't agree on the epsilon, then that can't be a correct guess.
Yeah, so we just return a value of these x values to epsilon values, and we know that since epsilon has to go through these specific rules, there are some values that aren't possible. So what happens is we have a what's it, bijective? I think we have a mapping of many to less. So there won't be as many epsilon values as there are x values. We expect 250 unique x values, but only 100, spoiler, 127 epsilon values. Because some epsilon values have different x values. So what we do is we calculate that, and we do, let's full screen this for now.
Sorry, I think the word you're looking for is surjective.
Surjective? Yeah. It's one of the jectives, that's for sure.
A bijective is injective and surjective, I think. But I don't know. I haven't done linear algebra.
I hate maths, man. I don't. Okay, so we just do this for every possible fault row, okay? So we generate 4 sets for each row. So this is different between the row that we were working in before. So we got zeros, 1, 2, 3. This is just 0, x0, x1, x2, and x3, right? And each of these is one different byte for the group candidate. So this would be one byte in the key, this would be another, this another, and this another. And they reflect the bytes here. So x0 would be this byte, x1 would be this byte, x2 this byte, x3 this byte. So we go on.
Sorry, so I guess trying to wrap my head around this, and also I guess might be helpful for people who are just joining in. If you go back to the PDF, there's four cells that are grayed.
Yes.
Those are the cells that are affected by our fault, and we're trying to use the information from these 4 gray cells to get 4 bytes of the key. So that's why we're only looking at four things right now.
Yes.
Okay.
Exactly. And the reason why we do 4 calculations is 1 for each of these x values. So we generate 4 separate mappings with 4 separate mappings for each value of these x rows, so each possible error byte. Then so the comment basically states what I was getting to. There's only 127 unique values, and we build up a mapping of all the possible values of x to these 127 uniques.
And the 127 unique value is directly because of the linear equations we talked about earlier.
Yep.
Yeah.
I'm not feeling like explaining that bit. Just accept this bit. If you want to know,
if you want to know why
it's
exactly 127, there's a lot of math behind it.
Yeah.
But just all we care about is it's not 256. If it's 256, then we can't do no better than randomly guessing. Like, if there's 256 possibilities, that means that we can't do anything better than random guessing, because randomly guessing, we have 256 possibilities for each byte of the key, right? But now we say, like, oh, we've already, like, just with one of these samples, we reduced our search space for this one byte of the key to 127. So we already reduced our search space for one byte of the key by half, and then we can do better, right?
Hopefully. Okay, so yeah. We can do better, believe it or not. So we go through all of our tables, and the main property here, right, is that we're only interested in epsilon values that appear in all 4 of the equations, right? So we want x0, x1, x2, and x3. They all have the same epsilon value. So what we do is we we build up a bunch of intersection mappings. So what that is, if we look at ZMap here, what we do is there's a lot of bracket shit right here. If you look at rows, all we're doing, right, is for each row, we go through every possible X value and we add it to the Z map. And the Z map is just an array of these values, and all it is a possible candidate and an intersection. And what that means is if you add an intersection for a row, it basically marks it like, yep, okay, row 0, this value appears in row 0, this Z value appears in row 1, or whatever row it's added to. So we go back to, where were we? Down here.
So you're building a bit mask.
We are building, yeah, we're building a huge table of all possible Z values.
Right.
And we are marking which ones appear in which row here. Okay.
So the reason why you're using a bitmap is because it's easier to do the intersection later. Is that why? Like, I'm just wondering, like, what this step is.
So for any candidate, we only care about ones. So for every, I'm confusing Z and X maybe, as Z and epsilon a lot, but they are the same thing. And we only care about Z values.
Let's just talk about Z. We don't have
I'm
to
calling them all Z now. This is a funky Z. So these Z values, we only care about ones that appear in every single one of these. Yeah, so it has to be values that appear in each of these
What do you
rows.
mean by every one of these? Like, what is these here?
Can you see my cursor?
In the context? Yes.
Okay.
Yes.
So these are.
But like in your code, what is these?
Okay. Yes. So we have a mapping of these X values to these Z values. So now what we want to do is figure out, okay, which Z values appear in every row, every one of these zeros. So if we're calling a row is x0, x1, x2, x3, we want to find out which epsilon values appear in all three of those solutions. Yeah.
I'm wondering why you need that when you already know which x values, because of your that mask you created earlier, right? Was each group.
Yeah. So this is what's producing this map, this mask, right? So we're going to have some epsilon values that are unique. Like some solutions work for an individual solution, yeah? So we might have this equation here. It might produce 1, 2, and 3. This one here might produce 2, 3, and 4. This one here might produce 2, 5, and 6. And the bottom one might produce 2, 7, and 8. We don't really care about Z values that aren't in all three of these, because it has to the Z value has to satisfy all of these equations. So what we're doing here is we're marking, okay, which ones are in each, which Z values are in each of these rows. We're calling these things rows for lack of a better name. It's very confusing, but we'll call all of these equations rows. So we're basically looking for all the Z values that satisfy all of these equations.
Right.
So we just mark it. We're like, okay, this satisfies this row, and then we add the candidate to that Z map. So we're starting to build a tally of the opposite relationship. We're starting to build invert our original X to Z map and start producing a Z to X map. Because at the end of the day, we don't really care much about the Z value. We care about the fact that it reduces our problem space down, but the X value in the end is what we can use to generate the final key. So if we get this, all we have to do is XOR the output. Well, if we figure out X, basically we can calculate the key, because then we can calculate we can use the S box, and then we can calculate the XOR, etc., etc. Not too important right now. We'll get back to that. But the important part is that we care about X more than we care about Z, but we care about Z to reduce the number of possible X's. You have 4 equations with 6 unknowns. You brute force all X naught to X3, so 4 equations only. 2 unknowns remain, epsilon, epsilon prime. The unknowns are X and epsilon, but yes. So once we've gone through all that and we've tallied up all the Z values for each row, we then only care about the ones that are intersected, which, and all that means is all the Z values that appear in all of these equations. If they appear in all the equations, they're a candidate. They're a possible solution for that byte. So we actually calculate 4 solutions at once. Yeah, 4 possible solutions at once. So we each time we get a solution, it's a possible solution for each one of these. And that's where the attack comes from. We massively decrease the amount of effort needed to calculate the keys. So we basically just take all the values, put it into the candidate list, and it's done. Then if we pop back here, we repeat the same thing. So this is again just for where the fault is located. So this is assuming in row 0 here. The next one's going to assume in row 1, row 2, and row 3. And all that does is generate a ton of candidates. And if we then go back even further to our top level, wherever the hell that was, here. So we know E prime is good, P plain text, XOR faulty, plain text, unknowns are X and E. So yeah, 4 equations, 6 unknowns, 5 unknowns, then X0, X1, X2, epsilon. 5 unknowns. Yeah,
5 unknowns,
that's right,
but
yeah.
also it's very important that we are in GF2 to the 8. So
yes.
that helps us tremendously in terms of brute forcing the final
Yep.
variable. I think there are ways to solving an underrepresented system of equations where even in the reals or complex
Yeah,
number space that you can do easily when you have
that was
this many.
originally how I was trying to solve it, but it is just so much easier to just compute all the possible values and eliminate which ones aren't possible.
Yeah, so if we were to zoom out on what's been presented so far,
Yep.
it's essentially an algorithm for solving this system of equations with a little bit of brute force to make up for the unknown variable, right?
Yeah.
For the extra unknown.
Yeah. So
Okay.
what we do is on the high level, we have this of 256 possible values for each of these equations. We just build a huge mapping. We know there's a relationship between Z between all of these equations, and what we can do is we can just really quickly through this mapping just eliminate ones that aren't possible. We then end up with a bunch of solutions that could be possible, and we just keep those. And the idea is once we have those solutions, we can then intersect these sets of solutions together, and very, very quickly it reduces down to hopefully one solution. And once you have one solution, that's that. And intersects candidate is a candidate is just a set of x values, really. Like it's just a set, and all this is intersecting a set. And if sets intersect, then we basically just discard all the other ones that don't intersect. And
Can you explain a little more what you mean by intersect?
intersect, like literally, if a value belongs in, we have two lists here, two lists of
Mm-hmm.
faults. We have new candidates and old candidates. If some of the new candidates match some of the old candidates, uh, we discard everything except from those that map both. If none of them map, we just expand the list, right? So the idea is this list grows until something starts to match into it. Then we just very quickly eliminate tons of solutions. It's effectively, I guess, a voting strategy here. So the code, if I stop pressing,
Yeah, sorry, I'm still trying to comprehend this code.
even for a single equation, you can solve for x naught and e despite two unknowns. S x naught to e equals only some choices for x satisfy. Yeah. Yeah, that's the whole premise of this. Yeah. Uh,
Okay, sorry.
what's
So
up?
in your intersect candidates, um, I guess, yeah, can you just explain this again?
Okay, yeah. I'll show you what the intersect does.
Okay.
So, a fault candidate. I'll explain what a fault candidate is in this representation. So it's just an array of four sets, right? So we have four sets because we have each candidate is a possible solution of z, and each z is a solution for four values uh, of the key, right? So four
Right,
x
right.
values. So
Yeah,
every one of these epsilons maps to four of these. So this is all that is. It's
right.
representation of these x values.
Okay, so it's just a mapping. Okay, so I
Yeah.
see. Because if you know Z, then you can retrieve 4 bytes of the key
Yep.
because of our equations. So you're just creating a map of
Yep.
those. So you can
And
easily solve it,
whenever,
right?
yeah, basically, if there's two lots of, it's effectively intersecting on this rather than the values, right? But it's more of an implementation design here that we're just creating sets of these values instead, discarding this value, and then when we go to intersect, we're just checking that uh, this each value of the sets intersects another one. So what we're really looking for is multiple faults with the same epsilon value. Yeah.
Mm-hmm. Mm-hmm.
And then that very quickly gives us a single. Oh, sorry, that's not true actually. Uh, we're looking for ones with the same x values for different epsilon values. That's my bad. Uh,
Right.
but consistently have the same one. So we are looking for basically the same bytes appearing.
So you
It's yeah.
you
It's
have
just
multiple Z values,
yep.
and you want to match them to the X values.
So let me maybe if I try to explain it. So a candidate is a z value to a bunch of possible x values,
Mm-hmm.
four specifically. And then what we do is we'll end up getting like a bunch of these z values. So we'll have like
Yeah.
z1, z2, z3, z4, and we don't really care what these are. But really, all we're looking for is like, okay, uh, we'll get all these z values. These are valid, and what that then builds is like, okay, so each column then becomes a set. So this is like a set. I don't have enough space, so we'll just use S. So this becomes a set. This becomes a set. This becomes a set. Because these are all possible solutions for each byte, right? So it could be any one of these X values. Like the key. Does that make sense?
Sorry, let me just think about this a little bit.
Sure.
Uh,
Problem is, right, while we can reduce the search space for these Z values to get the right X value, because the X value is what will give us the key in the end. So while the Z value lets us eliminate a lot of possible X values, we still have quite a lot of them.
Right.
And these Z values they are different faults that produce valid solutions. So the key value for the first byte in the group could be this X, it could be this X, it could be this X, or it could be this X. But we know that whatever X is, it's going to be the same ones for all of them, right? Because if we find the correct fault...
Okay, so maybe what I'm not understanding here is where are you getting these 4 Z values? Like what is the source of them?
So if we go back to differential fault, and we're building up these candidate lists, so we calculate a Z map, which is a mapping of Z values to X values. And in this is our candidate. So we store the X value and which equation it belongs to, right? So very quickly what happens is we start building up a mapping of where did I put that? Z values to 4X values. Always 4. Can only possibly be 4. Yeah, any Z that doesn't appear in a column, we don't care about. Because we have the Z value has to solve all of these equations. Yep. So what happens is we end up having a list of candidates which basically follow this idea. It's only these values here, but the idea is that one single Z value produced 4 possible solutions. Then a second set of Z values produced another set, third set, because there's going to be a lot for just a single one.
I see. So essentially, okay, so I guess so these Z values are not necessarily your inputs. It's like it's like you're continuing in your pre-computation. It's like another step, right? So you
No.
haven't.
Sorry, continue.
I guess maybe the question I'm trying to ask is, at this point, are you using your inputs? Like,
yeah, so we are using the inputs, but the inputs only affect the relationship here, right? So what we're building is the inputs are used here, right? To build the calculate potential values. So if we look at back to X to Z map, it's the first value passed in. It's our differential, and it is just used to calculate.
Right. Okay,
what we're doing is we're just going through all possible values of X and calculating what error value would satisfy.
Right.
This equation, right?
Right. Okay. So I see. You generated like all the
possible ones
Z
for
values
each equation,
and now you're trying to reduce that large solution space to like by trimming out all the like impossible solutions.
Yes. So we do it in 3 steps. So
I see.
First thing we do, right, is we calculate all the possible solutions for a single equation, right? So we have this here, and this is all the possible solutions for this. Then what we do is we calculate all of these. So that's what these rows are. These are all the possible solutions for each one of these equations. Then we consolidate all the same. We start building a mapping of all possible error values, not error values, z values,
That values, yeah.
and add in the x values. So this is actually an optimization step. We can just store
Right.
the x values into the candidate list as we generate them. Some of these candidates won't be valid because they won't have a z value that falls under all of the things. So this is where the second level of elimination comes into, right? We start trimming out all the z values that don't fall under all of these equations. Yeah, so that we start. The first step is we eliminate all the possible. Actually, we don't eliminate anything. We start building up a relationship. Then we eliminate all the non-possible. Really non-possible, David? Jesus. All the impossible solutions. So we filtered those out. And then we're left with a list of candidates that satisfy these.
That satisfy all the equations. Okay, I see.
And that looks like this. The z values aren't important, but these are the ones that made it. So maybe 3 didn't actually make it. So what happens is you have a gap here. It's maybe like 4, and then it's maybe 8. Yeah.
Right. And is this where you end up with 127 possible z values?
No. You end up with 127 possible z values from the get-go, but not all of them fall under every.
Right. Okay.
Yep.
And is there like, does it always end up with like a certain number, or is it variable? Like after you apply these steps.
I don't know. It seems very closely related to around about 30 or 15.
Right.
But I think I've seen sometimes it being 1 or 1 less.
Right. Okay, that makes sense. Yeah.
Yeah. The problem is I don't have huge data sets to do this, and I've not generated.
Yeah. No, I think that there's like, if you look at the proof, there's like 3 possible cases, and it doesn't matter. You don't have to scroll to it. It's beyond the scope of this, but I can see like 15 or 3 or
no.
so on.
The proof is kind of important, right? Because if it's actually it's not that important, but there is. So what happens is this is the reduction, and the math's not important, but for z values, there are 2 possible values, and then there's 4 possible values, right?
Yeah.
So really, what this is a set of values, and in each set, right? Okay, this is where it gets a bit weird. There is 2 or 4 solutions for each byte.
Yeah.
Okay.
Yeah. That I don't think we can explain without.
I can explain this easily, but
yeah.
If you're interested, generally,
your OnlyFans subscriber content will get the full explanation.
There's multiple x values suitable for a single z value. Basically, yeah, a single z value generates multiple solutions for a single byte, either 2 or 4. And then what the intersect does is it goes through all of these, right? And whenever there's an intersection across these internal ones, across all 4 of them, yeah. So we're looking for. Let's actually just build an example up here, just to make everything a little easier. Copy paste. Maybe I should call these ones Y just for the hell of it. So I actually think I can explain this easier enough.
Okay.
We'll try. Wait. I want it to line up. Easier to read. Okay, so we'll look at 2 because you actually only need 2 for it to work. Actually, let's do 3. Let's have one that doesn't work.
You sure you want to use Z again?
Oh shit, yeah, I don't want to use Z. Let's use what's your favorite letter?
Well, no.
You
No,
get P.
that's bad. T. Okay,
You
yeah,
can
P.
P.
No, you can't just. Oh, I thought you were gonna press replace all.
P goes brr. Okay, so what we have here is we have a bunch of possible candidates, and let's say we got really lucky and 2 of these solve the key. This solves 4 bytes of the key. Sorry, like this is to be clear. This solves 4 bytes of the key potentially.
Yeah. Yes, everything so far we will only solve 4 bytes of the key.
Yeah. So let's actually call these B0, B1, B2, B3. So these are for different bytes, and all the intersection is right is it goes through the list of B0s, and it checks. Okay, are any of these X values the same as any of these Y values? And if they are, okay, you go to the next one. Are any of these X values the same as any of these Y values? If they are, you go to the next one. If any of these X values are the same as any of these Y values, if they are, you go to the one after. And then if any of these X values are in this Y, then you have a solution.
Right, because
Because you have a complete, what would you call it? Intersection.
yeah, like any of all of the index element wise set intersections must not be null or the empty set.
Yeah.
Because you are, if they are, that means that the 2 candidates don't agree on a value of Z.
Exactly. So it gets a bit more complicated if then the same holds true here. So what happens is, let's say X satisfies everything here, and it's all the first values, but then this second value works here, this first value works here, this value works here, this value works here. What happens is you then have to discard, let's say there's Z5, Z6, there's Z7, Z9, and so on, all the way up to Zn. What happens is you keep doing this, and so maybe the first round you get these. Okay, let's go through the scenario here. Is Z4 solves Z1. Okay, so let's say the first set of candidates we get are these 2. We're like, all right, cool. We don't have a solution here. So what happens is if I reference the code here, what happens is if none of the new candidates intersect the old candidates, we just copy over the list, right? Oh, sorry, the opposite.
The list.
If none of the candidates intersect, all we do is we append the new candidates to the old candidates. So it starts off, we have an empty list of possible candidates. If we go back here, so after the first round, we have this, none of them intersect, so we add that to the list. Then, actually, this is a lot easier if we do it maybe like here. Then we get
so
Z.
this is an optimization, because the other way you could have done it is you could have just said like, oh, like I'm gonna do like n choose 2 and try like every possible 2 Z values and see if they have an intersect.
So yeah, you could do it like that, but as soon as you start flattening these relationships, you get more solutions and you need more inputs to solve it.
Right.
You need to maintain the groupings.
I see.
So we do the next set of candidates. We get Z5, Z7, no intersection, so they're added. Get to Z8. no intersections, so they're added. Then we get to Z9. Then what happens is if these intersect Z1, and let's say uniquely, so only one value in each set match, yeah,
then you'll have a non-empty set.
then you'll have a non-empty set. And what we do is we just discard all the candidates.
Yeah.
We put the intersection in, and if the intersection ends up
Right.
looking like this,
That's pretty smart actually. Yeah. Yeah. So just to be clear, this this optimization I don't think has anything to do with the this attack specifically. I think it's just a nicer way of 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 doing your solution space reduction in a I guess a faster way. So this is an algorithmic optimization that's not necessarily um
yeah,
like not necessarily something that would be in this
it's
paper, right?
no, it is. It is.
Do they propose this?
They don't propose it, but they definitely suggest it. It as soon as you go through it, it feels natural to do it this way, right?
I see. Yeah.
But yeah, so if you get to Z9 and you get lucky and there's a 1-to-1 mapping, you end up with this. Like, this is the only thing in your list now. Your candidate list is a set of one value, one set of values, each of one value, right? That's a solution. That's it solved. So if we go back to the algorithm, which is DFA, and we look at solved, all it's doing is it's checking that the candidate list is size 1, and if it's not size 1, it's like, no, it's not solved. You need one solution. And then all it's doing afterwards is then, okay, we have one solution, but is there one solution for each byte? If there is, it's solved. You've got it. You've solved the key.
Right.
In the weird case, you can end up with a solution like this. Yeah. So maybe yeah, let's just call it Y. So this wouldn't be a solution yet, but you'd still. Oh, maybe this is a mistake. So what I do is I discard the entire list. So let's say we get through to this. Z9 intersects Z1. So what I do then is I discard the entire list, and the candidate list becomes this. Oops. Yeah, no, it has to be because they're values that agree on each other. Yeah.
Yeah.
Then very quickly there'll be another one that solves this. Hopefully. But you could be smarter about it as well. Like this. So if I go back to the algorithm, I think we're done because these are just the same but for different groupings. Then what happens is I return the key candidates, which should hopefully all be solved. And if we go here, we have to talk about this SBox stuff, but yeah, so it checks if they're all solved. So it's not that interesting actually, but yeah, actually let's just talk about it while we're here. So if you look here, there's a huge comment about the relationship. We know X at this point. This is what the value we've solved is X, the same X in this algorithm here.
So just to zoom out a little bit, what you're discussing now is how to go from the X value you just found to the actual key, to the actual round key.
Yeah. So what we're doing now is like, okay, so we've got an X, but we want a key. So let's figure out how to do that. And the relation, is there a nice equation on this?
So the X here.
Oh, there is no nice equation. Okay, so in general, if we go back to the AES algorithm, we are here. We have an X value that goes into subbytes. It's gone through shift rows and everything. We know the position. You can mix these around however you want and you'll get the same results. What we've got is a X value here that's already been shifted. So we don't need to do a shift. So all we do, actually, ignore that. We've got an X value here, right? We've got 1 byte of the AES state.
Just to be clear, the X value corresponds to the AES state at round 9.
Yes, yes. At the end of round 9.
Yes, end of round 9. Yes, after add round key.
Yep. So we've got the one. Well, actually, we have the entire AES state here.
4 bytes of the AES state, not the entire state.
No, the entire. Bytes. We have the entire AES state because this is a solution. Okay. In this case, we have the entire AES state, right? Because we have all 4 groups solved. So that's 4 by 4 bytes. 16. That's the entire AES state.
Okay. Yeah.
So what we need to do to get a key is we can't get this key because if we get this key, we need to know the state before, obviously. But we actually know the ciphertext because that's the output. So all we have to do is
XOR the state.
We have to go through the subbytes, we have to go through the shift row, and then once we XOR that result with the ciphertext, we get the round key.
Nice.
So how I do this is, since we've stored all the X values, we take the reference, so that's the ciphertext. I copy it into this key value, and this is effectively the fault index stuff. It's an abuse. I should rename this, but that's your shift rows. Yeah, because we talked about how if we go back to the encrypt, all these positionings is just a column state affected by shift rows. So the fault index is shift rows. So all we do is we shift the rows, XOR it. So we've got the ciphertext. We're going to XOR it with the S box output of the value for each group. So there's only one solution. That's why all these are zeros. Yep. And this is for each group. So this would be so the fault index is the fault location in the linear, whatever. It's the location in the output. So
just backing up a little bit here. So earlier we talked about how you can only get 4 bytes.
4 bytes.
So at this point we already ran, everything we talked about before. 4 times was 4 different sets of round 9 faults. So at this point we have 8 different faults, or 8 different faulty ciphertexts that that we are looking at. 4 different faulty ciphertexts at 4 different locations.
Yes.
And the correct plaintext. So we have 5, ciphertexts we're looking at, and we applied the previous thing 4 times to get all 16 bytes of the state. And then using those 16 bytes, you're able to reverse the linear step of AES, the shift row, and get the final round key out of it.
Kind of. Not reverse, actually forward. So we have this state here. The subbytes is this bit here. The forward box is just plugging it into the S box. I call it forward box because for decrypt, it's not the S box. It's whatever progresses the algorithm forward. So for decrypt, that's the inverse S box. For encrypt, it's the standard S box. And the fault index is so the way this works is we get, for each group, we get 4 bytes solved, and those bytes correspond to the places we take them out of. So the fault index is 0, 7, 11, 13, and that maps to this. So it's the first byte, 7th byte, 10th byte, 13th byte.
Yep.
So that's where we know where to put them, pretty much. and that is the shift rules effectively. So we don't need to do anything explicit for that because it's just intrinsic to this operation.
Mm-hmm.
Where were we? Here. So yeah, we just XOR it. So this is in the key is the ciphertext. So this is just a small optimization, you know. We don't, or not really optimization, but yeah. The ciphertext is in there. We're doing the XOR of this state here with this state here. So all that's in the key is round key 10, which isn't the final key for an encrypt. So for an encrypt, you have to then reverse the key schedule back to key 0. But for decrypt, that's the final key.
So for those who don't know, I guess I'll just briefly talk about the Aes Key
You want to talk about
Schedule.
the schedule? Okay, okay.
I mean, I'm not going to talk about the details. I'm just the only thing we care about is that the Aes Key Scheduler expands a single 128-bit key into 10 128-bit round keys. But the important thing here is the operation is completely reversible without having to know any other information. So for one given any round number and the round key, you can derive all the other round keys. This is why AES only has 128 bits of security, even though it technically has 10 128-bit keys that are used in the algorithm. Which means that, you know, even though we only found the round 10 key or the round 0 key or, you know, whatever, we can retrieve the full key just by, you know, doing a bit of the reverse AES key schedule.
Yeah. It's trivial to reverse any round key back to the...
Hashtag trivial.
It is. It is. It actually is.
Yeah, I
The
mean,
key
you
schedule is
can use
very
a
straightforward.
standard, yeah, just use a standard library for key scheduling,
Yeah.
honestly.
Yeah, so then what happens is it spits out the key, and that's it. So, what should I talk about now? There's a few nuances here. We got, so explain DFA. That's how DFA works. There's a few
On
other
round
things
9.
we do on round 9. Yep. This paper here is completely based on round 9.
Yes.
So let's talk about round 8, which is what we did for the PSP. What I did.
So let's get okay. So let me do like a brief summary here, just in case not everyone was following the whole picture. So with round 9 fault, what you need, so you need to do a precise fault on one byte of the state in round 9, and with that you can retrieve 4 bytes of the key.
Yeah.
Then you have to target another byte that is not within the set of the 4 bytes, you know, that you found the previous one, and then you can get a second 4 bytes. Then you can do the third 4 byte, 4 bytes. So in all, you need to precisely target 4 different bytes of round 9 state, and those 4 unique locations must not intersect with you know, the bytes that matter that we presented earlier was the mask, right? So in practice, that's not, I mean, it's doable, but it's not ideal because you need to have these like very precise control of like which byte you're corrupting. And we found in practice, it's very, very hard to control that. You essentially get like a random byte corrupted. It's really hard to control. Like, okay, I want to first, you know, corrupt byte 1, then 7, then 12, then 14, right? So there is an optimization. So this is kind of an extension of an attack. And instead of corrupting 1 byte in round 9 4 times, you corrupt 1 byte in round 8 once. And using that one corrupted ciphertext and the correct ciphertext, you are able to synthetically create 4 different round 9 faults that will work with the algorithm presented. So I think that's the big picture, right?
I mean, that's the detail as well, really. Like, yeah, it's hard to like you're when you glitch the AES. Typically, what happens is you get like a few hotspots where you can tweak whatever knobs and variables you've got, and you can change the glitch a bit. But it's very difficult to have like a scalpel to choose which uh like which row you're glitching. So, or sorry, column. Because yeah, for round 9, you need a glitch in one column gets you only 4 bytes. So you need to be able to corrupt not just one column, but this column, this column, and this column, and that can be really difficult. You might be able to rely, like, once you find a glitch, in my experience, once you start
The other
faulting,
important thing is that you are in the round 9 only attack, you cannot corrupt multiple columns.
yes,
And that is actually pretty difficult to do
yeah,
in practice.
it's very difficult. Yeah, I actually, well, it's very easy for me. You know what I'm saying?
You
Skill.
sure. I have to clarify my previous statement in case someone actually cares.
Yeah,
But what I mean is that you can have, other bytes corrupted in other states as well, but you have to make sure that all the faults corrupt all the same bytes, and you have to do this 4 times. Was like, say you in your first set you are targeting like byte 12, and the second set you're targeting like byte 8, but you're also corrupting like byte 4 for some reasons. Well, then you have to make sure byte 4 is corrupted in both your you know byte 12 attempts and your byte
sure.
8 attempts. So it does get like a little bit harder to tweak, because you have to like precisely be like, okay, I need this condition and then this condition, and you have to do it 4 times. Not impossible, but
It's yeah,
um
the like you can probably do it. Like if you've got enough variables to modify, you could probably get it. The way I like to think
yeah.
of it is like each glitch is kind of reliable. Like once you glitch something, you can like reliably glitch the same location,
Yes.
right?
Yes.
Uh, and how I like to think of it is like there's little notches, right? Little pits where like okay, so if you change a value, you might glitch this byte here. And then if you glitch it, you might change the value, but it'd always be this byte. Then if you tweak the values, it doesn't necessarily mean you're going to then glitch this byte or this byte. Typically, the way I saw it was I glitched a byte, then I can change tons of values, like very incrementally, and I would not change the byte location. But eventually, I'd start glitching this byte here, completely missing over a column, which would make
Mhm.
a round 9 target infeasible. So
Yeah.
round 8, if you glitch one place, the way it works is if you look at the algorithm, right? We have gone through all the shift rows and shift bytes, but you could just take the results from round 8, shift rows them, and replace it and make it like a fake round 9. But then you have a glitch in every single column. So you can
Right.
solve it with only a handful of round 8
Right. So
glitches.
the important thing is you have a glitch in every single column, but now you splice in your
Yep,
correct ciphertext
yep,
to essentially like, wipe away the columns you don't care about.
yep,
And then you can do this attack. I think that's the clever part of the round 8
yes.
transformation.
So that's literally all we do here, right? Is for converting a round 8 to a round 9, we go through this, we loop through the, what are we looking through? We loop through the fault, and for every round 8 fault, you get 4 round 9 faults, one for each column. Uh, and you go through if an R8 fault falls into this mask, and the mask is the Dfa blend mask. So if we go back to encrypt, the blend mask is this, yeah. So we make 4 round 9 keys, where every F is a round 8 byte, and every
Every
O
0
is a round 9,
or O
is a reference byte, sorry.
is a reference, yeah. So you're just splicing it to
You're
the
just mixing it
faulty
all
and the
up, yeah.
correct.
You
Yeah.
build these, and you get 4 round 9 faults. Effectively,
Yep.
the way you just weave in the R8 fault into
Yeah.
from the reference, it's very clever. Yeah.
Yeah.
And it works. And yeah, so what we have here in this is round 8 faults. That's why we only need 3. And yeah, easy. So
Yeah.
round 8 fault, easy peasy. The hard part is what we do. It's called turkey analysis.
Yikes. Okay, wait. Let's hold off on that for a second. Let me just briefly
Is
talk about like a couple of other things that
oh
people might be wondering
yeah,
about.
what are you thinking?
So this is only applicable to AES 128, but for AES 256, like we did on the
Yes.
Vita,
Yep.
then you have to basically do so, instead of 10 rounds, you have 14 rounds, right?
Yep.
So targeting, round 9 in this case would be round 13, and round 8 would be round 12. Everything works exactly. But in the end, you only get half the key. You
Yeah.
only get 128 bits. So remember when I said you can reverse your like Aes key schedule by giving any one state? In Aes 256, the key schedule is a little bit different, and you need actually 2 consecutive
Yeah.
states in the key schedule in order to reverse the key schedule. So you need like the round 14 and round 13 key, or the round 0 and round 1 key. And to do that is actually, quite simple, because once you have, the final round key, or the 0th round key, you just do one round like backwards, right? So a decrypt 1 round or an encrypt 1 round. And now you can think of it as you just have another AES, but like with 1 round stripped off. Then you can do this whole attack again, and then be done. So in practice, we targeted round 12 first, and then we got half the key. So then we took all of the samples we corrected, and we reversed 1 round. So now all our samples, all our round 14 ciphertext now become round 13 ciphertext. And then we use a fault on round 11 and target the
Yep.
round 13 ciphertext. So that's how you can get 2 different round keys. And but with that, you need 2 faults instead of 1 fault.
Yeah.
But yeah,
So yeah, the reason
trivial.
why that is the case is because even though the AES algorithm has 256-bit key option, the state still stays 128-bit, right? So rather than generate so for like AES 128, it generates a key like on each value. So key 0 is the key. Key 1 is based on key 0. But the way it works for AES 256 is it kind of works, and it still maintains the 256-bit. So key 0 and key 1, they're your input. Key 2 is based on key 0. Key 3 is based on key 2. And it keeps that grouping all the way up. It doesn't mesh them together really. And that's why you need the 2.
Yeah.
Correct? Yeah.
Yes. So I guess we can talk about turkey analysis now. Do you want to
I love
pull up?
turkey analysis.
Do you want to pull up my paper
No.
where it's actually presented
You
instead
presented
of?
it so badly though, so oh, I've upset him. I'm sorry. I'm sorry, Ethan.
I've already unfollowed.
No. Don't follow me. Your paper's actually okay. I actually understand it now. After all my DFA studying. Like, this shit, yeah, I'm like, haha, yeah, I know this. In fact, it goes even further. I understand your big equations wherever they are. These ones, I understand these now.
Nice, nice.
Yeah,
That's
pretty
okay.
cool.
So yeah.
I think this
So
presentation
that
was
is,
ass
yeah.
though.
Equation 3 is turkey analysis in a nutshell.
Yeah,
But don't worry about that. That's the academic version.
yeah. We're
I think,
not actually going to look at this. I'm only flexing
yeah.
Ethan's paper. But
I think the important thing. No, I actually want you to look at the graphs
oh yeah,
in that paper, because that gives the reason why you need to do this, and it's something that no academic has touched upon. I think if you go up a little bit, and you probably have to zoom in, there's a distribution graph of those two.
yeah.
You can zoom into those. So the one of the main problems of these like round 8, round 9, like all these faults, is that the way they model faults from an academic perspective is that you have a uniform distribution of the possible bytes or bits that get corrupted. So it's like with equal, it's like equal probability you get no fault, or you get a fault in bit 1 or bit 2 or bit 3, etc. And in practice, that's not true, because it's like there are certain bits in the state that are much, much more likely to be corrupted than other bits. And you see what happens is, it's like, in one sample, you might have bit like 11, 12, 14, and 17 flipped. And then a second sample will have like 11, 12, 13, 15, and 19. And then like 11, 12, 13, 14, and 22. But it's like every single time, 11, 12, and 13 will be flipped. And then like, the chances of other bits are getting flipped is like different. And usually under like this assumption, if you don't think about anything else, you can't apply these like round 8 or round 9 attacks, because we require precisely one byte to be corrupted and no other bytes. But fortunately, we don't have to do that. And there one weird trick that will annoy all of these computer scientists who spend all their time trying to chase after the least number of bits or most number of bits flipped and still able to retrieve the ciphertext, and you don't have to write like a 40-page PhD thesis on it. The one weird trick is, instead of using your correct ciphertext as the correct ciphertext, you take another faulty ciphertext and you just tell the algorithm that it's correct, and then everything works out.
So in layman terms, after ignoring what Ethan just said, you just use each of the faults as a reference against the other faults.
That is literally what I just said. That is literally what I just said.
Just ignore what Ethan said, all that gibberish.
Ignore what he said. I'm
you
just gonna say it again.
You just get all the faults and use it as a reference against everything. Then DFA till goes brrrr.
DFA machine go brrrr. But actually, that is actually what happens. Is
I wasn't listening.
Yeah.
You did mention that it can reflect in bits flipped in the actual key.
Yes.
Okay, cool.
I mean,
Yeah.
that's what you. Yeah. But I mean, we found this by accident, because
Yeah.
we were just like fucking around. Like, what if I just use a faulty text instead of the correct text? But turns out that worked. And my paper gives a mathematical proof for why it works, but you don't need to know that.
I'd like to point out that I found it. Only, not because I'm a genius or anything, although that's true. But because I didn't
don't
understand.
Rewrite history.
I didn't understand
Don't rewrite history. I actually found it. I was
You did find it, yeah.
I was the one who
I like the way I found it though.
I ran all the scripts, and I messaged you saying, "Hey, something weird's happening. I'm able to get the keys even though I'm not using the right ciphertext." And then you wrote a script to automate that
No,
process.
no, no, no. I definitely found it
Yeah.
as well. Like not understanding what the fuck you were doing because at that time Ethan was just polluting the chat with like gibberish, and by gibberish I mean like very technical, glitchy stuff. Uh,
Okay. Yeah.
and the only reason I found it is because like, can you try and find a solution for this thing? And I had no idea how to work his tool at the time, so I just put things in random order.
Fucking.
I found it. Ethan found it by like calculate observation. I found it by chance. Tell me what's more interesting. Nah,
Yeah,
for sure though.
well,
It's very cool. The Ethan's turkey analysis.
yeah, sure. But it's funny because it's like all these paper, like, in the past 15 years, they've been racing each other for like, oh, how many bits can we corrupt and still retrieve the keys, right? And it's like, oh, this paper you can corrupt like 16 bits in round 8, and then someone's like, I can corrupt 4 bits in round 7, I can corrupt 2 bits in round 6, I can corrupt like 28 bits in round 8. So technically, you know, with turkey analysis, you can have 128 corrupted bits in round 8 and
Yep.
still retrieve the key.
Yep.
They just have to be the same 128
Yeah.
bits.
It's nice. Yeah. So like these keys are only solved by turkey analysis. Like if you run it through the algorithm without doing turkey analysis, like it doesn't work. The actual
Yeah,
reference doesn't solve it. You have to use one of the faults as the
yeah,
reference.
yeah. And once again, the reason for that is because it's almost impossible to only corrupt 1 byte in the
Yeah.
state.
Yep.
You are going to be corrupting many bytes in the state, but
Yep.
luckily, a lot of these bytes are highly correlated with each other.
Yes,
So once
and
again, statistics win.
yeah, because if we look at it again, we need to assume that all these are zeros. So if we get lucky and something corrupts here and maybe like here, there's a good chance that this corruption's the same.
Yeah, yeah,
That's
and
the
then you
way I think
XOR
of it.
them,
And
and
you
then you
XOR them
XOR
and you get
them.
zero.
Yeah,
Yep.
and it still works. But it's the technical way to describe it is that it's the DFA analysis that was done is linearly invariant, or it's invariant to linear transformations. So you can do as many XORs with the same thing as you want, and it'll still come out correct.
Correct.
But let's just call it turkey analysis, right?
Let's go ring. So yeah, it finds keys very quickly, this tool. So if we go to the paper and we
I mean,
copy.
but actually, your tool like outperforms Phoenix AES, which is the only known public tool, by the way, by like 300, 400 times, right?
Uh, Maybe. Phoenix AES is good. Uh, that's what
Yeah,
we
Phoenix
use.
AES is literally the only non-academic like every like there's actually no other DFA tool that exists like publicly. And I think all these academic tools are just so bad that nobody ever publishes it.
Mm.
Um So in the effect, there's actually two. There's another one that is kind of garbage. It's like a C++ one. Like I don't even
Hey,
remember
come
the
on,
name of
bro.
it. Not yours, like another one.
Yeah, I know. I know.
Um, but but yeah, this is the only one, and it's frankly annoying because this tool is based on the original ASDFA paper, and none of the papers from the last 20 years have a open source implementation that you can just download and run. So, you know,
I found another sample. Oh, oh wait, maybe it's an encrypt.
yeah. It's encrypt.
It's encrypt. Wait, last round key. Yeah,
Yeah.
yeah.
after 50 milliseconds. Lol. Can you time yours? Can you just like run it like with like time?
I mean, yeah, it's showing the elapsed time.
Oh, look at that. What is that? 2 milliseconds?
Yeah.
Yeah, two.
But
Literally 20 times
the
faster.
benefit of it is it scales with the turkey analysis. Because the turkey analysis is
Oh,
expensive.
that's right. Yes,
Because,
because you have to try like all possible permutations, like and pick three.
yeah.
Yeah, the way we did so the Vita hack, the way we did it, and this is actually on our GitHub, is that we literally like so let's say we have a sample with like 1,000 collected samples. We do 1,000 pick three and try all possible three combinations, and until the key is returned.
Does any of this
Uh,
translate to non-AES? It doesn't
no,
really, no.
yeah, so DFA is applicable to most, if not all, symmetric and asymmetric algorithms, but you need a specific it needs to be like the DFA algorithm for each cipher has to be specific. So
Mm-hmm.
for asymmetric crypto, you're usually targeting one of the like for RSA um, DFA, you're targeting one of the Montgomery multipliers. I think that's one of the earlier ways people do it for triple des. Because of the FIFO structures, you can actually defeat DFA countermeasures by so DFA countermeasures usually just do an operation twice, um, or by like encrypting and then decrypting and then checking the result with your input. And the idea is you can't, you know, if you if you corrupt the decrypt, you can't corrupt an encrypt. If you corrupt an encrypt, you can't corrupt a decrypt, or it's like very hard to, right? But because triple des has this FIFO structures where encrypt and decrypt share um the same hardware, it's actually easier to target um like a encrypt and a decrypt. So you can actually do a double fault and get it. And if I were in a PhD program, I would totally do this and publish it as a paper, but I don't have the time for that. So someone should steal this idea and, and get them published.
I actually
But
did a. It's not related, but you said double fault, and that reminded me of something. For Kirk, for the PSP crypto engine, Kirk 7 is just a straight AES. Okay, so it just needs a single one. But uh, for Kirk 9, right, it takes a seed in. It doesn't take a seed. It takes a it's a key derivation function. It takes in 128 bits, and judging by the traces, the amount of time it takes, it looks like it's an AES up. And yeah, I think so. I could easily calculate like the final AES key it generated, based on the input. So like if I put in all zeros, I could calculate the key it would have generated. And if you analyze if you make a huge set of these keys, it wasn't linear. It's like
mm,
so I was like, okay, so it could be a hash, but it looks like it's AES. So I tried to
yeah,
double
doing
glitch
AES
it,
twice.
and I almost got there, but I couldn't get enough samples for the last set.
Uh,
Because as soon as you start double glitching the PSP, it starts crying, all the timings mess up and everything.
yeah.
Anyway, yeah, that's just a
Yeah.
story.
You can probably try clock glitching instead of voltage glitching, right?
So yeah,
Like
clock glitching was weird. I couldn't turn off the PLL. I could only just change the
right.
multiplier. But so you'd expect it to filter it out, right? But I actually did manage to get some weird uncontrollable effects clock glitching.
Yeah. Yeah.
So maybe there is
There's
something
probably
there.
like some secret
Yeah,
undocumented register to bypass it, but yeah, it's too much hassle.
yeah. I mean, yeah. Even with the PLL enabled, I was still managing to like make the system crash through clock glitches. But yeah, it's weird. I couldn't get it to do it reliably. Oh, I could get it to do it reliably, but I couldn't get it to do it in a way that did something useful. In general, it's quite hard to get the PSP to do anything useful because as soon as you start glitching it, it just crashes. Uh, it's like the window of glitching is so short before like nothing happens and everything just crashes.
Yeah.
So if I actually show code now, if I talk about how I glitched the PSP, because I think we're done with DFA for the most part.
Yeah, I think so. I guess final thoughts for me is I think it's actually very, very nice that DFA works with like only 3 samples, because if you remember on the Vita, we had to do like for reasons I don't want to get into right now, we had to do like a huge set of AES brute forcing, like
Yeah.
2 to the 38 brute force to get 1 sample because the engine wasn't returning like the ciphertext directly. So we actually had to spend like quite a lot of AWS cores, like 72 core systems to generate these faulty ciphertext.
Yeah, not ideal. Okay, so since the PSP was so fragile when I was glitching it, right? Like the the processor would I wouldn't get any input from Kirk. Like I'd set up a decrypt, I would glitch, and what would happen is nothing would change with Kirk. I'd figured out where the AES was happening because if you take a if you do a trace, right, of doing 0 bytes of encryption, 16 bytes of encryption, 32, etc., you can start seeing the trace where like what's obviously changing, right? Because these things are fairly deterministic. The power traces look mostly the same. Uh, but when I was glitching Kirk, I was expecting to see something change. I wasn't expecting it to be like super accurate, but nothing was changing. And when I increased the glitch length, the processor was crashing. What I ended up having to do was uh, start Kirk asynchronously. So you tell Kirk, okay, work asynchronously and throw the CPU and interrupt when you're done. And then I had to sleep the main processor using this not supported function in GCC. And what happened was this is like a sleep function, puts the core to sleep and it wakes up on an interrupt. And then I would glitch in between. So it would trigger low after I put a trigger high. There, I'd wait on the chip whisper for like a certain number of cycles, then glitch when the processor was asleep. And that actually managed to get me Kirk in the end. This is probably the bit that took the longest, other than the very last bit. Uh, yeah, it took a while to get a glitch that actually worked on the crypto engine, just because the MIPS is so fragile. Uh, Now he lies. He's missing Kirk 2 and Kirk 9. Kirk 2 and Kirk 3. Those keys aren't very interesting. Yeah, we don't have those. They are unused in the operating system, so they have 0 value.
But Davey, you didn't get all the keys then.
The other ones we're missing is
How can you call yourself a hacker when you didn't get all of the keys?
so the other one we're missing is, I'm trying to think, 5 and 8, which is the unique key one. So every PSP has a Kirk command that does unique encryption for personalization. So when you install the firmware, it overwrites a bunch of data in the executables with this personalized encryption. So you couldn't just like copy the firmware and decrypt it or whatever. So I managed to figure out it's a very simple function. It's very short and it's not much longer than a standard AES operation. So uh, I assume it's just an XOR, or maybe just a. It's longer than the Kirk 7 stuff. So I assume it's not like a baked key, but maybe it's like a XOR or something. I don't know. Uh, that must be a big key. Or I could be looking up some register or something else. It's longer but very short still. So it's not like a complicated derivation. So I was hoping if I got the glitch working on hardware today that we could take a look at that one and see if I compared data points. Maybe there's some obvious linearity for two samples. And then we can try on a third to see if that works, but we won't bother with that. But you know, it's unique keys, not that important. Key 6 and key 9. Kirk 6 and Kirk 9, sorry. They're they're only used for, I think, save data and some, what else? So hibernation data on the PSP Go. Yeah, not particularly interesting again. The good thing is, like, if there was specific key values, I could just derive them, because like if a save data uses a constant, which it kind of has to, I could calculate all of those. But save data is not that interesting, because well, emulators and stuff just ignore encryption. They just null it out, because what's the point of encrypting the save data? Yeah, and that's all that's left in Kirk is those three functions: Kirk 2, Kirk 2 and 3, Kirk 5 and 8, and Kirk 6 and 9. Um, did you get all the VIA PSP keys? Yeah, pretty much.
Yeah,
Uh,
I mean, it's obvious what Pluto was asking, but
yeah,
like there's just people in the chat, like these trolls, that's like, but not all the keys.
we're missing the battery handshake
Stupid.
keys for service mode. Yeah, I mean, we're missing all the Cisco
Yeah,
stuff.
it's
We're
like,
missing
yeah,
some
we're
BitLoader
missing the
stuff.
Wi-Fi chipset encryption, frame encryption keys. We're missing the
Oh, we're not though. We got those.
oh yeah, we got them. Yeah.
Yeah, we got them.
There's also like the gyroscope controller.
the
There's some,
the
yeah,
power
application stuff.
controller. Yeah, yeah.
Yeah,
I
it's
wish I could be
so fucking
higher.
like, yeah. I mean, yeah. There's this con CV. There's a lot of stuff that doesn't really matter. Like, okay,
I
so
mean,
I
they
mean,
matter, but they're not.
from a broad perspective, I think, there's like two things, right? You either get the keys as like a CTF kind of thing, or you get the keys because you want to decrypt some stuff. And I think, like the real stuff that matters, like anything that can decrypt any content that Sony will ever encrypt, past, present, and future, we can do. And I think, that's good enough for all intents and purpose, right? The other keys are like nice to have, like CTF challenge
Yeah,
kind
yeah,
of
they're
things, but
nice.
they're
Yeah,
like,
I
it's
mean
like,
that's
yeah,
pretty
whatever.
much my attitude to it, right? Like I've done DFA on the PSP. I got a bunch of keys. Like I'm
Yeah.
done. Like
Yeah, like,
the rest is just
yeah,
repeating. Like I could probably
yeah,
get
exactly.
Kirk. I
Yeah.
could probably get Kirk 2 and 3 because Kirk 2 is an encrypt, and I can get the result out. So that's DFAable.
Yeah. Like
So
hack a new device. That would be my advice. Like
yeah,
don't
I'm
don't
I'm
try don't
looking for
try
something new
hacking the
now.
same device over and over again.
Yeah. So yeah, and the main reason for doing this whole streaming stuff was actually a DFA tool. Like I decided, okay, maybe I should. So originally, right, I didn't need to know anything to do DFA, like literally nothing. The most novel thing I did. Hang on,
Back up a
hang
second.
on, let me finish. The most novel
Okay.
thing I did for getting keys on the PSP, right, was figuring out how to glitch by sleeping the processor. That's probably the most specific and unique thing, right? The rest of it was just plugging scripts in, really. I didn't like I don't mean like it's ultra trivial, but like I didn't need to know the internals of how DFA worked, like with existing tools.
Okay, I
But
think for some of your audience, I mean, I know like lots of people here like are
yeah,
aware of it, but I think it's important to point out that I actually did like go through those all those papers, understood it, and I coded up all the tools. I wrote our custom chip whisper
yeah,
like FPGA. I wrote all the Python
uh-huh.
scripts. right? And I dumped all the stuff, and then you helped with, like a lot of the partial busting stuff,
Yeah.
and then we were able to like get out the keys. But when you did the PSP stuff, all that's all
Yeah.
those tools were available,
Sorry, yeah,
and
that's
I
what I was
was
trying to get the point across, right? Like, once all the tooling was there, like, architecting DFA for a different system was just uh, all the novel work is just getting the glitches out, and then it's the same tooling afterwards. Like, you plug it into the same DFA solver, and that's it. It's kind of nice.
but also like for me, like the biggest challenge, why it took me like 6 7 months was because there's just not really like a community or like people who you can like talk to, like, hey, I'm running into this problem, how do you solve it?
Yeah,
And like very basic stuff, because most people don't document like the more basic like setup related things, like, oh, like I'm getting noisy measurements, how do I reduce that? It's not interesting enough to put in a paper or a blog post, so people like ignore it. And but then you also like you don't have other people who you can like talk to, that's like, hey, I did this as well, like, here are the
yeah.
parameters I use, here's the tools I use. So I think ultimately that is like the more difficult part, is like trying to wrap your head around all these different papers, all these different tools, and figure out like what's what.
My
So
issue was like, I don't enjoy reading papers because usually I understand what they're getting at, and I can understand them when I put a lot of time to think about it. But like, you look at Phoenix AES, and it's nice, but the if we look at some of the code,
yeah, no, I did not understand their
it's
code. Like
like
I understood the paper and I could not understand this code.
the code. I mean, it works, but like, there's not a whole lot of explanation what's going on. It's like fault
Yeah,
maps. What does this mean? Like, if you're
yeah,
new to DFA, and I guess I was new to DFA, like I knew how to run the script, sure, but I want to like proper have a real understanding of it. Like, so like, even looking at this code, like I very quickly gave up because it's like, hang on, I don't. What's a fault map? Like stuff like that. Uh, okay, these are obvious. The multiplication table is also obvious. These are just the AES ops. That's fine. What we got? Key rewind. Yep, fine. That makes sense. Uh, check. Okay, that's checking if someone falls into a grouping.
again, we
That
don't
made
need a dunk on me.
no. I'm saying it's good. Most of it's good, right? But it's when you
Yeah,
get to the uh algorithm, like getting the candidates and
yeah,
stuff, like all this stuff here. It's it was actually where is it? The candidate calculation itself had
yeah, it's
zero
very dense.
explanation,
Yeah,
so it was hard to learn from it. So I very quickly gave up. Like even stuff like converted R8 faults, it didn't
yeah,
make a lot of sense to me. So I then went on to this is where DFA tool came from. Was like, okay, I'm trying to learn how to do this so I can explain it to people, and explain it to myself. Really, like this is all self-learning kind of thing. So a lot of this was just like, then okay, so if I just ignore everything else, just look at the paper and try to figure out how to solve it, and hopefully, I'm hoping DFA tools somewhat clear for those that the paper is hard to digest. Like this stuff is, I mean, the paper is good, right? This stuff is really nice, like explaining how the faults are propagated, but the actual calculation, like if you're not, for me, I have to sit down and think quite hard when it comes to proofs and stuff like that, and understanding.
you don't really need to
You
understand
don't
the
need
that
to,
proof part.
but if you
It's
want to, like you have
But I
to
mean, it's
think
not even
hard.
like I the thing about the proof is that you don't, it's kind of like an appendix almost, because it all it does is it tells you like, yes, we can do this, but the
Actually,
fact that you actually get results is, is enough you need to worry about. The proof just says like, yes, for all possible cases this works, but it's like, if I just want to do this, even from like understanding it, I don't actually need to know that yes, this indeed works for all cases,
for me,
because that's
it
that's what the
was
proof is saying.
yeah, okay, yeah. I don't mean specifically the proof, but like the analysis is merged in with the proof, right? Like, and it's very easy to
Yeah.
get lost in it, I would say, for me, someone like me. Uh, I mean, if I sit down and think about it really hard, which is what I ended up doing, as well as just like bouncing it off other people, uh, yeah, you understand it, but like it's very obvious how it works. Like you first look at it and you're like, okay, so there's an obvious common factor here, and that helps you derive it. But for me, it was like, how do I then coerce that into whatever form? And you don't really, you kind of get an idea of what's going on here. Like all this stuff doesn't matter, right? There's a few common parts that matter. Like these parts are very important, and yeah, like you don't need it for the most part. But
Yeah, like the
I would
propositions
say,
you can take at face value. You don't have
yeah,
to understand
yeah,
the propositions.
and yeah, for me to understand it, I thought it would be easier to
And
have,
also, like for someone who reads a lot of papers and proofs, you the way you read papers is you usually the only time you actually have to like or you should read the proofs is if you're reviewing the paper,
yeah,
because honestly you just assume that yes, the proof is true and I am not the one person who, of the millions of people who read this paper that suddenly found like a fatal flaw in this proof, right? So you don't actually ever have to read proofs for papers unless it's like a paper specifically about a proof, or you want to read a proof in order to get idea for like proof techniques for your own work, etc., etc. But in
yeah.
papers like this, I don't read the proof.
Yeah, I mean, I definitely did not read the proof or test the proof or anything. The main idea was like, okay, so it went through this, and then I got this function, and then it just splurged out data, and I was like, hang on, how do I then get this data? For me, that was the kind of like, oh, okay, how do I do that? I don't understand what's going on here. Where does this data come from? And yes, it's explained, but it's explained in a very academic way, I guess. Mathy.
I mean,
I, it's
yeah, I don't know how else they
yeah,
would explain it.
yeah. I mean, how else would they
Uh-huh.
explain it? So for me to understand it is, I guess, it's just down to the way different people learn. For me, the easiest way for me to learn it was just to try and implement it. And okay,
Yeah, no, that definitely helps me as well.
okay, yeah. Looking back, I initially I would have said that I thought my implementation was much clearer, but after doing this, it doesn't seem like it's that much clearer. Like there's still like a lot of confusing terminology. The comments are there and they're okay. Like I explain why I'm calculating this thing, which I think is the main part, but I'm not really explaining all that well why I'm creating an intersection, why we care about the intersection. Yeah, like stuff that we've gone
Honestly,
over.
I think like if this was like a university class, this would make like a pretty good like final project assignment,
Mm-hmm.
right? Like because yeah, like I get those all the time where it's like, okay, we're giving you the solution, but you're gonna have to implement it, right? And then you figure
Yeah.
out like how much you lack in the knowledge as you're trying to actually implement it.
At the very least, now after doing this, I feel very confident in.
Yeah, you can put DFA on your
Yeah,
resume without feeling like
yeah,
a liar.
exactly. Get that DFA interview and be like, "Yep, I got this."
Yeah.
Yeah. No, it was good actually. So here's my advice to everyone. If if you want it, just implement all the things.
Wait,
Reinvent the
y-
wheel.
your advice is not message Ifan in the chat whenever you run into an issue.
My advice is also message everyone you know that's smart because their input's valuable. See, I said something nice about you, Ethan.
Smart or Ifan, I think, is the
Oh yeah, whatever.
yeah.
Yeah, that's pretty much it. Anything else we want to go over? I will. I'm not going to try and fix the hardware tonight. That's just we'll rule that
Nah.
out. But I do want to
Yeah,
just do some live stuff.
I
So
am so happy that you did not spend this whole time
yeah,
fixing the hardware.
I'm so pissed off though, right? Because I wasn't going to re-implement the code. Like you see, I've got the final code here. I was just going to go over it and generate a bunch of stuff, and then we were going to just go together and like go parse it all and be like, okay, yeah. That kind of sucks. Yeah, I got it all working last night. I even tested the glitch and I got values out. And I was like, all right, I'm all sorted for tomorrow. So this morning I was like, all right, better set up the stream. I plugged in the chip whisperer, but then as I swung around on the chair, I got like caught the cable and launched the PSP across the room.
Fucking Papega.
Yeah, and like it could be I fucked the PSP. Honestly, I might have accidentally pulled off a pad or something.
Yeah, dude, I don't know.
But what I'll do is I'll offline. I'm gonna go and have a look, see if I get it working, and then if I get it working, I'll be very careful not to break it, and we'll do another stream, and we will, it'll just be a short one where we fuck around, glitch some shit, get some keys, maybe play around with Kirk 8, and call it. But yeah, like if anyone wants to go over the code or something just now, we can do that. Otherwise, I think it's a good
If
time
there's any
to
more
stop. Yeah, and
questions in the
questions.
chat, yeah, I will probably head out to make lunch soon. So
Yeah. Any questions? Anything you want to see in the code? Whatever. And all the other code here is just simple stuff. So there's like a XOR stuff for 1 to 8 values. There's a class for 1 to 8 values, which is just a standard array of bytes. A set, is a set of 4 values or up to 4 values.
It's a hard concept to grasp.
Yeah. The rest of the stuff's very straightforward. AES tools is just a bunch of constants and numbers and calculations and stuff.
Yeah.
No questions?
I understand your code now, so if I
Yeah.
ever have to steal it in the future, then
Yeah, you don't
I
need to be
can
scared of
do
the
it. Yeah.
templates. The templates are it's there so when I implement all the different modes, I can just shove them in. So I plan to implement 256 and I guess maybe 192. If I'm doing 256, may as well do that as well.
Yeah.
But it's really straightforward. You just you just solve another set of problems, key one at a time or whatever. Yeah. If there's no questions, I guess we'll call it.
Cool. Follow twitter.com/ifanlu for more DFA content.
Yeah, sure. What should I DFA next? I want to DFA something. I need to find some piece of hardware that's not like a microcontroller, but actually something.
PS4.
PS4, fuck off.
Nintendo Switch.
Everyone's done the PS4.
Kappa.
No one's done the Xbox though. But
The Xbox One? Oh, you're never gonna hack it.
I hear it's got
completely.
actual hardware mitigations for DFA.
You are never gonna hack it because as soon as you try to, Microsoft will just hire you. So
that's the strategy, right?
that is.
Although maybe see the thing about Xbox or like a phone, maybe a phone would be pretty fun. Just hack open like one of my old Samsung phones or something. DFA, assuming
If it's Qualcomm, it's so fucking easy. Yeah.
Apple,
You can
YubiKey,
try.
YubiKey.
YubiKey.
That is actually interesting. A UB key.
I yeah, I think like smart cards have a lot of
Yeah,
protection. Like what I think what would be interesting if you attack a device that is known to be DFA protected.
that's what I was thinking, right? If I could try and
Yeah.
like find a way to DFA something that's DFA protected,
Yeah.
or try the fancy method, the other attack that isn't like a round 9 fault,
S
the the SFA,
SIPA, yeah.
yeah, that'd be quite fun.
Yeah.
And
No,
it would
that's
actually be quite,
SIPA is literally DFA endgame. It's
yeah,
impossible
yeah,
to it is actually impossible to defeat it.
yeah. I want to try that, and it's just a small modification to this, really. Instead of values, are just probabilities.
Yeah.
Yeah,
Yeah. It's actually I think like even easier because you're like you're making guesses directly on the state rather than like trying to figure out the value from faults.
yeah.
So yeah.
The end game is the DFA where you don't need any faults
Wait.
at
You
all.
don't you can't do DFA without code execution. That is strictly not true because
Mm, yeah,
if you know like all you need is to be able to see the ciphertext. That's it, right?
yeah.
Like,
You just need to be able to observe. You don't even need to know the plain text.
yeah. What SAPA? I don't know what that is.
Or maybe he's asking if that's what we meant. It's SIPO attack DFA. Where the hell is this paper?
Uh, fuck. I have it in chat. Let me.
Wait, I just clicked a link and it's your fucking paper? Get out of my Google.
Ah, fuck.
Is it SIPO?
Maybe
I thought it
I
was an
got
F,
the.
but maybe I'm wrong.
Wait, I'll pull it out real quick.
Yeah, I'm going through the. Yeah, it's a super cool paper.
Yeah, it's all the like within the industry, it's kind of the hot thing right now.
Yeah.
Yeah. Fuck, where is it?
It's just all I can see is you just misspelling it apparently.
Yeah, yeah. Yikes.
Oh, we've lost it now.
No, I found it. I found it. I found it. I'll
Oh,
post
good.
it in chat.
Yeah, please. I'm gonna bookmark it so I don't have to lose it again.
Yeah, it's SIFA.
Yeah, SIFA. Yeah. Okay, cool.
SIFA. Yeah.
Yeah.
But just, like a quick tease since we can't get into it, with SIFA, you you don't need to observe any faulty ciphertext. Like the only thing you can observe is a non-faulted ciphertext. So there's only two conditions that needs to be met. One is the device reacts somehow whenever a DFA is attack is detected. So whether it returns an error or shuts down the chip or returns like junk data, like it just have to do something different whenever it detects a fault. That's the only thing that's needed. And then all you can see like the non-faulted ciphertext. So just like like the working ciphertext. And then you just do a statistical attack, and then you can get the full key. It's insane because then you're like your toolkit for all future devices is a does it have DFA protection? If not, then do DFA. If it has DFA protection, do SIFA, and you can get any key out of anywhere regardless of any protection. Caveat being, if they physically try to detect every means of fault injection, which is not possible, then we'll still be screwed. But yeah, so end game of DFA.
I might actually implement this on
I mean,
PSP.
you should. It's actually the thing that's impressive is this paper that I presented is so readable. It's like
Yeah.
you all you need is like first year statistics. Like you don't even need like like the super advanced like machine learning statistical knowledge. It's like all you have to know is like
It's
what is a
yeah,
statistics test, right?
it's
Like what is a
amazingly presented.
chi-square test, and then it's like bam, get all the keys. So
Yeah, I should implement this. I should, if I get the fault working on PSP again, I should implement this so it's there
yeah.
so I could test it. I mean, it's pointless on the PSP because we can actually just do real DFA.
Hack another device, dude.
I wanna hack another device, but
Hack any other
maybe
device.
it's better to get like the tool working with data I know that works. Keys I
I
know.
mean,
Oh.
test was your own generated data,
Oh, I
right?
could
And
just do
then
that, right? Yeah.
yeah.
Yeah. Yeah, of course, yeah. Just yeah, what the hell? Yeah, I could just generate the data. That's what I ended up having to do for most of DFA tool. It's just like
Yeah.
plug out a bunch of uh faults. It's pretty easy. Yeah, no, I want to find a new device. I don't know what. I definitely want to do something modern though. I'm not gonna get like an Arduino or anything. Kirk 2 would be nice. I don't want to waste time on it. I mean, if I get the PSP working, I might spend 10 minutes on Kirk 2. Like we don't even have data that like so Kirk 2 expects data to be formed in a certain way. And we don't even have a single example of a Kirk 2 payload. So like I if I couldn't figure out how to craft the payload, it's very similar to Kirk 1. But if I couldn't figure out how to craft the payload like within 10 minutes, I'd just give up, to be honest. Like
I'm
it's
gonna be logging off. Any last words?
no.
Okay. Well, good luck
Thanks.
with your future
Thanks for
DFA endeavors.
thank you. Yeah, I won't be around much longer, but I'll chat to chat
Yeah.
for a little bit
Okay.
till they
Cool.
stop speaking to me. See you later. Thanks for
Okay.
uh
See ya, chat.
doing some DFA.
Yeah.
If you need to craft a payload, you can use time attack. It takes more than 10 minutes. More like okay, yeah. Like if I have to craft a payload, I have to craft uh, a payload with a timing attack. I'm not going to do this. Yeah. Unless like if you've got if there's payloads about, then I'd consider it. But you know, rather not. Because if it is like Kirk 1, then the encryption will be last, so it probably won't come under. Wait, no, the. How does Kirk work? Uh, let's see. So Kirk, if I'm encrypting. Yeah, so the encryption is not hashed for Kirk 1. So in theory, right, it could be possible to get the top level key for assuming it's the same as Kirk 1. If there's a valid packet, it could be possible to trivially get the encryption key, right? Because the encryption's done last, and the signatures and stuff are just dependent onto it. They're not encrypted, or Yeah, they're not encrypted, and they're not hashed. Makes sense. The tools are available in Git. That's assuming you need a sample such block. Not sure you do need for Kirk too. I mean, see, this is a problem, right? I'm not. I'd be willing to do the attempt DFA, but I'm not really up for trying to figure out how to work Kirk to how to coerce it into accepting some data. I'd rather just have that. You see the problem? Like, yeah, like if I need to calculate a block, I'd just rather not do that. It might be that Kirk 2 doesn't give a fuck as well. Like, you could just chuck it some data and it'll calculate the hashes and stuff. I wonder how there's differentiation for Kirk 1, 2, 3. I don't remember the header having the Kirk type, but I could be wrong. I don't know. So there is usage of Kirk 3 and I think Kirk 2. So the P sheet executable in the PSP, it uses Kirk 2 or 3. One of them's the encrypt, and I think it's for like development, not executables, but development PRX stuff. I don't know. I've never seen any data. It comes from packages. Whenever a PRX is in a package that's installed via P sheet, so the game extra content or something, it does, when it's installing data to the PSP, if there's a PRX, it encrypts it with Kirk 3 and then or 2, one of the two. But it's the same as Kirk. It's like the same size of header, stuff like that. But I don't know the header stuff's already there on the executables. It's just passed in, and it looks like from the code in load core and stuff that it's the same structure. And the what is it, the message led or memlimed or whatever the encryption libraries are. It has decryption and decryption for PRX types of those, but I don't know. There's like not any baseline data to go off, and I cannot be bothered figuring out what that data is. Like, if it's not used, it's extremely less valuable. So I'd say if you want me to look at it, get some working data, and I'll test with that. But otherwise, no. I'm not going to bother trying to figure out how to work Kirk 2 and 3. Kirk 5 and 8 is the unique key. I will look at that. It's very simple. We'll see if there's any very obvious connection between the fuse ID and the key. I think that would be the smart play there. And for the last two, which is 6 and 9, it's not that interesting. It's more complicated. It's very complicated actually. It's almost like 3 times the length of, or maybe even more. I think it was like 3, 4, 5, 6, that kind of magnitude longer than normal Kirk. So I have a feeling it's very complicated. I don't think it's like simple like oh, this value goes in, it's encrypted with a special key, and that's your output key. I think there's some other circuitry going on there. Would be nice for collection. Yeah, sure, it's nice for collection purposes, but like this, at the end of the day, for me, there's nothing for me to learn. I'm not going to be learning how to do DFA. There isn't any real value. At least for Kirk 7, I could argue there is some value for emulators. So, if we look at PPSSPP GitHub. And if we go to pull requests, closed search by at the very least, it had some value because a bunch of games could then be decrypted that required pre-decryption on the PSP. So that's nice for it was nice for a bunch of, like, eventually PSPs are going to be faulty, not working great, and it's nice to have that original data being able to be replayed without having to like trouble yourself into decrypting it all. So that stuff had actual value, but stuff like Kirk 2 and 3 and Kirk 5, 8, and the last one, 6 and 9, like no real world value. So I have even less ambition to figure them out. Change Kirk 1 registers to Kirk 2. Kirk 2 block equal math friend. Well, Kirk 3 actually, yeah, true. Actually, Kirk 2 is encrypted, so you don't need to forge anything. You can crypt a block with Kirk 2, presumably. Yeah, presumably, but, you know, figuring out that stuff's part of the... Still missing KLE 4? I actually figured out a lot of KLE 4, okay? So, it's based off of ECMA. It's very... I managed to get most of it decrypted with ECMA, but it seems that they've used... Either I'm not understanding how similar all compression algorithms work, right? Which is... I'm not super versed in compression, so I could be completely wrong. But for compression, it seems like a lot of them are really similar. Like they just use the same kind of logic. Kaylee 4 and friends, they seemed very similar to LZMA. Minus like I think the way it is, it's like so LZMA. If we look at the source code, Linux. If we look at the Linux version, GitHub. Okay, we'll just look at this. I think. Oh no, fuck this. So in the Linux kernel, there's huh. It's RLZ base, aka LZMA. I mean, it's not correct, right? WSL Linux? Oh, this one. Like this is the thing, right? All compression's super similar, but the problem with it's not one to one, it's a variant. Like, yeah, well that's my point, right? Every compression algorithm pretty much that follows the same like run length stuff is super similar. Like all of them. And the closest match I could see was LZMA, and if we... What would it be under? Let's just search LZMA. Okay. Yeah, so what I remember is like the range encoder is almost identical between them. So like all these functions, they're super similar. And the only difference is like a bunch of these constants are different. So like I think these ones are all the same. The normalize, I think these are all the same. It's stuff like these ones, the model total bits. So all these customizations, they're all totally different. So I could easily compress some KLE4, KL4E even, just by modifying some of these values, right? And that would give me a valid a valid compression block as long as I didn't use any of the actual compression stuff. So like I could just encode literals quite easily. The problem was when it gets up to the matches and stuff. So all of this stuff, I was really struggling to figure out if it is LZMA, I was really struggling to figure out the right combination of these values that generated the same algorithm used for the decryption on for the KL4E, sorry. So maybe it's possible. I would say if anyone wanted to look at it any further, I got bored and fed up and realized not worth the effort. But I would say if people are really interested in compression and they want to look at the PSP's one, I would say this is a good place to start. Like, see, for example, like all of these header things, they just don't exist. All these LP, PBs, and LCs, these are like options. They're all constant and baked in. So if you look at some of the decoding stuff, you'll see it use these values. They're all constants. I can't remember what values they are, but you can easily brute force it. And then once it starts spitting out, oh, that's an idea. You could just brute force all of the constants. I don't know how long that would take, but yeah, like all these values are baked in, which changes the algorithm. So like wherever you'd see it use like here, wherever you see it use this, all you'd see in the assembly is the fixed number. Brute force constants, yeah. So like you'd see all these fixed numbers. So that's how I kind of figured out a lot of the values, but like the code's optimized as well, which makes it a bit more pain in the dick. But it's not hard. It just means there's effort. So this stuff worked fine. This is just a literal matching. It was a literal matching. Something like that. Oh, this is decryption. Sorry, yeah. Wait, yeah. No, this is right. Wait, so is there no run decoding here? Oh, there's the probability tables. Yeah. There's something else in there. Yeah, like all these masks and stuff, they're normally for LZMA like configurable within a certain range, but I found that if Sony does use LZMA, it's all pre-baked in. All these are one set of constant values, and I think that's what differentiates KL4E and R RZL3 or whatever the hell they are, KL3E, ZRLZ or wherever the other ones were. They're all the same algorithm. They're exactly the same algorithm, but some of the constants are different, and I'm fairly sure. While some of the other constants are different, the only ones that differentiate those ones are these values. And maybe the some of the like lots of these ones. So I think it's not these ones, but all of these ones here I couldn't figure out. These are all the ones that are used for the matching bytes stuff. And I know for sure that these ones were like, so KL4E, this value is 4. KL3, this value is 3. Like there is some mapping, but the code's compiled with these constants baked in and it changes the algorithm, and it's not super obvious because I think then some of these values become 0, and then some of the algorithm then looks really weird because lots of things don't happen anymore, but whatever. But yeah, I think if we've got no more questions about stuff, we'll just call it there. I will have a look at this PSP, see if I can figure out what the hell's wrong with it. I hopefully haven't broken it. If I haven't broken it and I fix it, I'll arrange to do another stream. It'll just be a short one where we get some keys out, get some DFA partials, not partials, DFA faults out, glitch some shit, and then call it. Get some keys, try something else, then call it again. What's this? Okay, so yeah, this looks like this guy's figured out it's LZMA as well. Oh, I just closed the windows. Yeah, so like all these values, these constants, depression algorithms. Yeah, so 0 range, set buffer to the end. Yeah. Okay, so it sets the code from the first byte. So the way I looked at this was, this is like the first step, like LC, like yeah, like some of the values are there. Yeah, this guy figured out. I mean, this could be my misunderstanding, right? But it looks like this guy's figured out. Wait, is this just straight up the algorithm? Decompress. Encode, yeah. He's got it. Wait, why do you need KL4E if you can just use this? Just update the constants. And KL4E, I think it skips a step. Let me have a look at my work. Yeah, I was trying to implement it in Python so I could have like all my other PSP stuff work with it, but it just, yeah, the effort was not worth the payoff. It would be nice. It was a nice thing to have, but like, yeah, not too big a deal. Where did I put that compression shit? Hmm. Can't seem to find it. That's what TP Unix decompiled from the PSP. Not sure which algo, but yeah, I would, if he's not sure, I would definitely tell him it's to me, like as someone who's not yeah, I think I might have seen this before. I saw a lot of code because yeah, I did ask on Twitter like if anyone knew, because I wouldn't say I'm very confident in knowing like how to identify compression algorithms very well. Most of the time, like you can just run like any like binary identification tool, and it'll tell you what kind of compression it is, because most people use the same thing. But yeah, I wasn't sure if it was like something pre-baked or if it was something custom, but I'm fairly confident it's LZMA with a bunch of baked in constants, but not sure. Did I find it? No. Probably have to grab for it, and that would take a while, so I'm just gonna leave it for now. But yeah, if anyone's interested in compression, that was my takeaway. Uh, it's it's very similar to LZMA. I have a feeling this dude knew that though. I think if he knew that, he would have figured it out. So it might not be. Hmm. Yeah, stuff like this as well. Like, I'm sure if I like thought about it more, it'd be easy to figure out, but nah. Yeah, the search isn't coming up with anything, so I'll leave it for now. But yeah, thanks for watching. I hope you learned something about DFA. Like anything would be good. The code's on GitHub. If you just go on my GitHub, it's DFA tool. You can have a look at it. You can test some values. I'll paste some values somewhere. I mean, there's no point testing values, but like, yeah, there's no point. But yeah, you can if you ever find yourself doing DFA and you get yourself some faults, you can run it through this tool and it'll calculate the key for you. At least for ES128, but I plan to add 256 at some point. Yeah, thanks for watching. Follow me on Twitter. Yeah, I think it's below, but if it's not, it's just DavyFTW again. Thanks. Bye.